All right. Good morning from Fairbanks, Alaska. Good afternoon, evening, wherever you are. My name is Carl Tape. I'm a seismologist here at University of Alaska Fairbanks. I'm organizing this workshop, which is really hosted by postdoc Bryant Chow, who's running most everything here. But we also have some great invited talks to kick off each day. I'm going to start with a sharing screen, just a sort of reminder of where some content is here. And you can, from the workshop webpage, there's a bunch of active links to the agenda. There's some day one recorded videos. There's surveys for each day that are really important for us to sort of document who showed up and what they got out of it and what they think could have been done better or what went well. Just to remind you, if you go to the agenda, it's kind of evolving. You can grab these papers in here. We're changing. There's an anonymous otter in here. You know how that is. These are open what you can see, and you can download any of these papers. So just click on them. So there's some background reading if you want the essential information. I've put these readings in there. I've asked the speakers to do them. So, they shouldn't, it's not like they're recommending, say, oh, read these papers. I really thought, let's find the papers and topics and have asked people to cover certain topics for this workshop, which is, I think really sets itself up well for the day. All right, so that's that part. And then under just a few slides although I've already introduced folks, and I'm not going to do the Zoom guidelines. Everything went great yesterday with up to 187 people we had, and everything went well. So I don't know, you could probably even have your videos on. I don't see any bandwidth issues so far. Raise hand, lower hand, respond to poll questions when you're asked, change your name to whatever you think you'd wear on a badge at a meeting, which probably wouldn't be like your Linux username account or something. But and so this is just to say, to start with, at the top, we have the sort of main developers of SPECFEM, SeisFlow's Piatoa software package. And then we have the workshop content dominantly put together and delivered by Bryant Chow. We'll see Akash Gupta also playing a significant role today. The software containers made by Ian Wong at Texas Advanced Computing Center. I put in main developers. I think this is a good segue to introduce our speaker this morning. So in the invited talks, we have Dr. Chinya Liu from University of Toronto, and really just in terms of the development history of SPECFEM, the adjoint capabilities, which give the foundation for seismic imaging, were done by Chinya. So that's in both the 3D code, SPECFEM globe. There's the equations that are laid out, and then the effort to implement these within a parallel code at the scale of SPECFEM and get everything done correctly. That's Chinya. So I think that's a remarkable legacy, that when we use these kernels that are buried under the hood in seismic imaging, that code was written there. And that's the highest level I can say to introduce Chinya. So that sort of impact on the code. So I'm going to turn it over. She's coming from Toronto here at Eastern time at noon. Thanks, Chinya.
Thank you very much for that, for the kind words. Let me share my screen. There you go. Hopefully you can hear me reasonably well.
Yep.
Okay, I'll go full screen. Yeah, is it good? Okay. All right, good morning, afternoon, evening, wherever you are. Just like Carl said, my name is Chinya Liu from University of Toronto. I was involved early on with developing the adjoint capabilities, basically this sensitivity kernel calculation for the spectral element code, both the SPECFEM 3D and as well the SPEC 3D globe. So I'll be very happy to talk a little bit about the theoretical background as well as the technical details, which will reflect on how you will be running it later on when Akash go through the tutorial materials. So yesterday, Jeroen and Daniel had great talks kicking off the first day of workshop covering the forward problem. So basically, if you know the Earth structure, whether it's 1D global structure or some complex 3-dimensional structures, you can use one of these packages, SPECFEM packages, to simulate how wave propagate through these models, so the so-called forward problems, with all these given advantages of using SPECFEM. Now, obviously, the next step would be, well, how do you apply this numerical solver, or a more advanced, accurate numerical solver, for the inverse problem, or in something I would call full waveform inversion. Now, there's a lot of probably confusion, and especially if you just enter the field, on the nomenclatures. So I myself think of full waveform inversion as seismic imaging based on a forward solver that's completely numerical. So whether it's finite difference, or whether it's spectral element method or finite element methods. So as also use a forward solver that's fully numerical, I would consider it full waveform inversion, because the numerical solver allows the full physics, the wave propagation physics, to be captured in the forward calculation, and hopefully also in the inversion. And then we've been using also the name adjoint tomography, which was trying, there's a particular flavor of full waveform inversion, as you'll see later on my slides, where I try to put adjoint tomography against some other flavors. And but I think the names have been kind of interchangeable nowadays. So I probably will be calling them interchangeably in this talk as well. So what are you gonna walk away from this presentation? Hopefully, I'll set up the stage for Akash to lead you through the tutorials of how to compute kernels. But first, I hope to give you a little bit technical, maybe a bit more equation than you want, on how do we compute kernels based on adjoint method. And also, if you do decide to choose your own misfit functions, how do you implement it, especially deriving the related adjoint source and then compute the related kernels. And thirdly, why do we need to, and then you'll see in the tutorial, why do we need to first run a forward simulation and then store the wave field, and then, or store the last frame of the wave field, and then run a kernel simulation. So that's why it's probably important to understand a little bit of the technical details to get to know why. So the imaging problem, when you think about what seismic imaging is trying to do, is saying, well, can you find the best model that would fit my observables, right? Whether it's seismograms I'm observing at stations, or some other sort of newer type of observations. But this is equivalent to say, well, can I minimize a misfit function, which kind of quantifies the difference between data and synthetics, so this chi function that measures the difference between synthetics, so S, and observation data. Now the synthetics obviously depends on what model you put in, or what the current model, initial model you put in. And with this, there's basically 3 questions you have to ask, right? Well, how do I parameterize my model? So how do I basically write this M? And also, how do I make this choice of misfit? And also, how do I search once I do define this misfit function, which I'm trying to kind of illustrate in this little graph here? It's this 2-dimensional misfit function. Well, how do I actually go down this misfit function curve or surface and find the best or the optimal solution? So how do I search for the best model? Now, there are 2 main streams, as you know, for any optimization problems. You can go with global optimization. In that case, you only rely on your ability to evaluate the chi function. So, give me a model, I calculate the synthetics, which is the forward problem you already know how to do, and I measure the difference. I compute the value for the misfit, and then I do many evaluations of that chi function, and hopefully I can find an optimized way to guide me to the minimum solution or the best model. Now, it turned out that's great, and that you can avoid local minimums, but it can also cause significant computational cost and may not be feasible for problems where the forward calculation is very computationally costly. So the other flavor, which is what we're trying to work on here, is the gradient-based local optimization. So you start from a solution, you say, well, can I figure out not only the misfit function value itself, but also what is the gradient of the misfit with respect to the model parameters. When you have that information, you not only know where you are in the misfit, but also you know which direction you should walk, at least generally, to be able to reduce the misfit function value. So that gives you some local guidance. And with that, hopefully with enough iterations, you get to the minimum value, the best model. But of course, it has a lot of issues if it's very nonlinear problems, or I guess it depends on how you define your misfit. When you have highly nonlinear misfit, you can potentially be trapped in local minimum. But that's I guess stories for another kind of longer presentation that hopefully in the future we'll have a chance to talk about. Like I said, for the gradient-based optimization, we need to compute the misfit derivative with respect to model parameters, this partial phi, partial m, at the current models, at the particular location of your iteration. When you go to next iteration, you have to recompute this, a new gradient. And then when you have the new gradient, you can update your model based on these local gradients, and then hopefully get the best model. And that's basically what Brian's going to cover tomorrow in day 3's workshop. I put some review papers on the FWI here if you're interested. And for those of you who are probably just entering the business of seismic imaging and probably heard the word kernels thrown around a lot. So what exactly do we mean by kernel? And it's actually a concept you do see in other sort of traditional tomography methods. For example, when you think about ray theory, high frequency approximation, where you're saying that the travel time is basically, or the travel time residual is integration on the ray, the slowness perturbation multiplying the individual length of the ray in, the length of ray in individual blocks, then you can write this as a big inverse problem where every row of this matrix is, the travel time of a particular ray is equal to the length of the ray on each block plus the slowness perturbation each block, right? So every row of this matrix formulation of the inverse problem is actually giving you a kernel. And that's telling you how sensitive each block is, right? The slowness perturbation each block is to the travel time perturbation you're seeing at the receiver. And you can, of course, write this as a d equal to gm and run through the standard least square inversion with regularization. And you also see it in so-called finite frequency travel time in tomography, where now instead of thinking the travel time as only sensitive to the slowness along the ray, you're saying the sensitivity is along a volumetric region around the ray. And so instead of just that thin ray, it's this volumetric kernel, so this Km. Here it's very famous banana donut kernels where we use cross-correlation travel time sensitivity. If you calculate the cross-correlation travel time and compute sensitivity, it's this particular shape. And there are actually many different sensitivity kernels that were used prior to the FWI or the adjoint tomography. But in most cases, they're restricted to 1D background models that made the calculation a lot easier. So you can actually afford to compute the kernels for individual measurements. And let me maybe just say one more word, and this will come back to we'll come back to this when we look at the numerical kernels as well. Is when you think about what these kernels are saying is, let's say for finite frequency measurements, I have the black as data, the red as synthetics. I'm trying to measure the cross-correlation travel time difference. And now usually if you have ray theory, you would be just measuring the first arrival t here and measure that shift. But for cross-correlation, and especially when you have a sort of a broadband arrival, and you want to make the cross-correlation measurements, and your measurements made basically over a certain window. So what this kernel is saying is that, well, can you tell me where are the places, where are the parts of the region of your model that such that when you have a source generating waves arriving at this location with let's say a single scatter, And then the scatter waves would then go travel back to the receiver. And this whole travel time, T1 plus T2, will actually be still within the window of that measurement you made. So even though you went ahead and made the measurement thinking, I'm just worrying about the arrival time, first arrival time, mostly related to the ray path. Well, actually, anything that's along the scatter path that would arrive within that window would still affect the measurement of a cross correlation, which is also kind of waveform based formulation. So because of that, instead of just sensitive to this ray path, you are actually sensitive to a region around the ray path where it's possible for the single scatter to create scatter waves arriving in the window. We'll come back. It's the same, basically the same thing as we'll see at the numerical simulation-based kernels. So one philosophical question you can ask here is, well, do I really want to compute individual kernels? Well, if you can afford to do it, it's actually a good thing, because then you can form the D equal to GM problem, and you can use all the traditional tools you have. But sometimes we just cannot afford it. And then we have to use kind of the global optimization formulation, as we'll talk about in a minute. But there are people who are trying to do it, even with full numerical simulation. So that's the so-called scattering integral method, where they use source receiver reciprocity to kind of save the entire wave field for waves generated from the receiver. So it's a completely different method, but still based on numerical simulations. But today we're focused on what SPECFEM is based on, which is the edge on state method. So just to go over what we wanted to do, we're given a misfit function. We want to compute the gradient of a misfit function, right? And the roadmap is we first start by computing not the misfit function with respect to the model, but the misfit function with respect to the synthetics, because the misfit function is measuring the difference between data and synthetics. So its dependency on model is primarily based on S. And then after that, we compute the gradient of S with respect to model parameters. And that's strictly just a single scatter or Born approximation. So some equations now. So let's start with the waveform misfit. So you've got the data, the synthetics, you're trying to measure the difference, and that's my misfit, right? And of course, the synthetics would change if you have a different model. So I can take the derivative. And now in this case, I know it's not exactly the derivative I wrote up there, but it's a variation because the synthetics is actually a function. So I'm taking the variation of chi, and on the right-hand side, you can see the only dependency on the model is S. So I have a variation of S here. So one way you can think of this, if you disregard the function dependency or the function aspect of it, is that this is basically partial chi, partial S, right? And you can see this relationship has to do with the residual between synthetics and data, which you will see later appear also in the adjoint source. So if you had used a different misfit function, then this term would be different. And then we use the so-called Born approximation. You don't have to understand the detail of this equation. All you need to know, if I can get my pen, is that it's trying to say that the synthetics is related to model parameters, density, and elastic tensor. Like Jeroen mentioned yesterday, that in this case, the model we're looking at is density and elastic tensor. So this Born approximation tells you how to compute this derivative of partial S, partial M, and it has to do with the Green's functions and the forward field. Delete that. There you go. Okay. So what do we do? Well, I'm sorry, maybe you can just go back here. What we do then is we insert this Born approximation, right, into this equation. And you can see, well, it'll give you a kind of a complicated form. And if you use the Lagrangian multiply method that Jeroen talked about, it's a bit cleaner. But in any case, you can see you ended up showing that the partial chi will be related to these model parameters based on a combination of the data residual, multiply the Green's function, and also the forward field. And if I combine the data residual term with the Green's functions, I can define something called the adjoint source. So this is an adjoint field. So this is basically taking that data residual and computing and multiply with the Green's function. And effectively, this is actually doing another forward problem where the source is given by the residual, not only the residual, but also the time reversed residual. And then, of course, putting in the Green's function just means that we're propagating that wave throughout the model, and you get the so-called adjoint wave field. Well, we'll come back to that T minus T. It's important when it comes to the technical implementation. But one thing you can see that is the link in the adjoint source with that definition of the misfit function that has to do with the residual of the waveform between synthetics and data. Once you compute these adjoint field, again, recall we're trying to link the misfit function with the model parameters. That with these so-called kernels, with basic derivatives. And these kernels will be a combination of model parameters as well as the forward field and the adjoint field. Now here is the acceleration of the forward field multiply the adjoint field. Now here for the elastic tensor, it's basic the strain. So this is strain for the forward field and the strain with the adjoint field multiply in the middle of the elastic tensor. If you look at these expressions, that these kernels are basically a time convolution of the forward field, so S, with the adjoint field, so the T and T minus T. And if you look at the literature, for a lot of FWI formulations, they would actually define as a correlation between two fields, so not time convolution. And that just depends on how they define their field or source over in this section on the adjoint field, whether they still treat it as a forward calculation or a backward propagation, but they're actually equivalent at the end of it. For that, so that's for the general expression for the kernels for elastic tensor and density, but you can also use isotropic media, and here the partial chi is related to the model perturbations through these kernels, so K rho, K mu, and K kappa, where K rho, K mu, K kappa are all expressions that's showing some time convolution between the forward field and adjoint field, either in the case of density of acceleration dot with acceleration of the forward field dot with the adjoint field, or in the case of mu, it's actually the deviatoric tensor of the forward field double dot with the deviatoric tensor of the adjoint field. And also in the case of kappa, it's the diversion or the dilatation of the forward field with the multiplied the dilatation of the adjoint field. All in this case, all time convolution. One interesting thing is we're used to look at density, p velocity, and s velocities. So you can convert this dependency, this model parameterization from rho mu kappa into rho beta alpha, and you can write out the dependencies. And as you'll see later, that if you're interested in travel time, it's not surprising that you'll get most of the sensitivities in either alpha or beta. And keep on coming back to this simultaneous access to T and T minus T. So when you think about what you need for implementing these kernels in a computer, you basically want to loop over, well, you're going to go through time steps, so T from 0 to T. But at every time step, you need access to T minus T of the adjoint field and T times of the forward field. But it turned out, well, if you carry the forward adjoint field this way and the forward field this way, both in memory, then what would happen is at any time instance, T, you only have access to forward field at T, which is what you want, of course, but also T for the adjoint source, which is not the time slice you want. You want another time slice, which is T minus T. So the way to solve this in our case is wave reconstruction for wave field reconstruction, but we'll talk about the technical details before we go into the tutorial. So that's hopefully giving you an overall idea of how these kernels constructed as time convolution of these two fields, forward field, adjoint field, where adjoint field is basically the wave generated by injecting some sort of data residual into the receivers. You can also compute the kernels for other type of misfit, for example, travel time misfit. Here you're looking at travel time difference between an observed and predicted from synthetics, the TRM. For a given model, you can take the derivatives. And here there's an interesting connection with the banana donut kernels, because if you just consider individual measurements, so TR at receiver R, there is a very known formula how to link that delta TR with the synthetics. So this is basically partial T, partial S. And with this formula here, that has to do with the velocity of your window seismogram, or window synthetics. And then if you define the window synthetics, in this case time reversed, because T minus T again, at the receiver as the adjoint source, and you can compute the adjoint field, which then give you the standard expression for travel time kernels. And in this case, if you had injected the S not as forward simulation from forward solvers, but as ray-based methods, then you're actually going back exactly to the banana donut kernels. But here we choose to use full numerical simulations. But I guess what I'm trying to say is this method itself is not a new invention. The novelty here is that the synthetics are going to be calculated based on full simulations. And then if we go back to here, if you put this delta TR back in here, and then you can see everything, all the formulations are exactly the same, except that now the adjoint sources have to also bring in the this residual, which allows you to basically simulate the measurement difference, as in here. You can also work with other type of misfit function if you like. So this kind, for example, frequency dependent travel time. So you're looping over all the receivers, but every receiver you have L number of bands. Every band you measure a travel time difference, and you add them up to define your misfit function. You just have to take the variation. In this case, you also have to figure out how to relate this delta TR with delta S, because that's the important step in order to then carry on with all the rest of the calculations for adjoint fields. Here, I'm using a generic expression phi I to relate delta TR with delta S. But if you have your own misfit function, figuring out what that phi I is the first step in order for you to write down the expression for adjoint source and adjoint field, and then implement it in the numerical code. And after that, once you figure that part out, everything is exactly the same as before. You're gonna write down that you're gonna inject your particular adjoint source, but then once you get adjoint field, you can time convolve that with the forward field, and you get your kernels. And even though these expressions are exactly the same, the difference in the choice of misfit function comes in to these adjoint sources, which are determined, of course, based on what adjoint field you define. Sorry, what adjoint source you define. Sorry. So the key to a particular source of misfit, like I said, is to write down the analytic expression, linking the perturbation of delta TR with delta S. There are actually a lot of quite a few different choices of misfit functions out there. I mean, sometimes the expressions can be so complicated, it deserves to have a full publication by itself. So here I'm gonna start showing a couple of examples of how this is done numerically in 2D, so both SH and PSD case. And I believe Akash later will probably allow you to run some of the examples that will reproduce similar results. So here we're looking at 2D problem, sources here, receivers there, homogeneous model. you basically get, if you think about SH case, you get the direct S wave, you get the SS wave that reflecting from the free surface. If you've got the PSV case, then you have direct P and S waves going from source to receiver, and then also surface reflections, PS, SP, and then PP and SS. Now, first look at the SH case. If I put in a Richter wavelet as my source, at the receiver, I'm gonna see the S pulse and SS pulse, where the S pulse is arriving around 40 seconds. Then if you recall that expression for travel time related, cross correlation travel time related adjoint source, in order to get that adjoint source, you have to basically take the velocity of your little pulse here, window pulse or S wave, which is in this figure here. And then you have to normalize it and then time reverse it. So instead of going to 40 seconds, you're actually going backward for 40 seconds. And that will be your S pulse for the adjoint source. And here's that where that time convolution comes in. So imagine from the source, you generate the forward field where the S waves just pass the receiver in the top at 44 seconds. And then you measure the difference like I just showed in that figure. You calculate the adjoint source and you can inject it at the receiver. Now, of course, if you recall in here, this adjoint source does not kick in until about 20 seconds. So the first 20 seconds, you don't really see much, but then later on, it starts to pick up. It starts to emit waves, and then it goes through and then back to where the receiver position is, sorry, the source position is, and beyond. So in order to calculate the kernels, we need not the same time evolution, but the opposite time evolution slices of these two fields. So forward field, so T goes up here, and this is the T minus T slices. Every time I take the T and T minus T slices from the regular and the adjoint field, I multiply them together in that case for the contribution for that time instance. You don't see anything at 44-second frame, but as you go back in time, you'll see these individual slits that contribute when you add them up to a full sensitivity kernel. So again, the way to think about these little contributions or where the sensitivity kernel is going to be, these are the regions where if you have your field going from source to receiver, which is this field, and then the field from the receiver going forward from as adjoint field, they would meet at a place where the total sum of travel time from source to that position and receiver to that position will be the same as that time window you picked for the S wave. And that's why it's not surprising that this kernel is right on or aligned with the S path, ray path, but of course with a bit volumetric shape to it because of the pulse you picked is a broadband pulse. So you will have a given window. So anything that would arrive as a scatter waves within that window would be measured. And you're picking up the sensitivity for all the scatters that would give rise to rivals in that window. So this is a figure showing the impact of model parameterization. So again, S waves, you can compute the density, bulk modulus and shear modulus kernels, and you can see for the S waves, mostly in shear and also in density if you formulate it this way. But if you convert the formulation to density beta and alpha, then the S kernels are mostly showing up only on the K beta kernel, but not on alpha and density. You can also compute kernels for other Misfit functions. So travel time we've already seen. For taking the shear modulus kernel as an example. So this is the SS kernel, and you can see the beautiful SS reflection from the surface, but this very nice pattern of the folded pattern at the reflection point. And you see this all the time for many other reflected phases. And you can compute amplitude kernels. So amplitude kernels is a bit different from the travel time kernels. Actually, it's a bit thinner in cross section, and which it's a different topic. We can, if you're interested in what the sensitivities are for different type of measurements. But you can also look at Q, which is shown here for S and SS. Carl's really known for making beautiful and really memorable graphics. So this is from Carl Tape's paper 2007, showing again the same exact thing. You have forward field going from source to receiver, and then you turn the adjoint field, which going from receiver to source backward in time. You multiply the individual slices. You get the contributions at each time frame to a full, what we call cigar-shaped 2D sensitivity kernels. So that's for only individual measurement from source to receiver. But if you got a lot of receivers, in this case in Southern California, we know there's a lot of receivers, and you take the residuals, inject it into the adjoint source, generate the adjoint field simultaneously for all these receivers. You won't be able to identify the individual kernels, but at the end of the day, if you go through the same thing, with travel time, with time going up for the forward field, adjoint field, you can get the interaction field and summoning up to get something called the event kernels. You won't be able to identify individual kernels in here very well, but you can actually start to see the actual underlying structural anomalies from these sensitivity kernels. One thing I need to point out is that even though it seems like you calculate a lot more measurements for travel time anomalies at all these receivers, but actually the numerical cost for computing this is exactly the same as the cost of computing individual kernels. One forward calculation, one adjoint calculation, and you multiply them slice by slice or time step summed up to get the kernels. And so that's what we call event kernel. So that's the misfit kernel for one event. But you can look at, in this case, 25 different events. You can then sum up the kernels, which will even give you an even better image of what the underlying target, in this case, phase velocity model would be. And of course, this is not exactly what the model should be or model update should be. You still have to iterate, and that's what, once you have the gradient, how do you actually iterate to get the best optimal model? And that's what I think Brian is going to tell you about in the FWI session tomorrow. I'm just showing here some examples kernels, so p-diffracted kernels, very interesting pattern at the coordinate boundary. S670 S kernels, very cool as a min-max phase X pattern at the 670 discontinuity. Also, I think in 2015, Carl worked with Lan, had this very interesting trapped wave kernel for a fault zone. So I think the kernels, of course, it's a one step going forward for doing the full waveform inversion, but it's also a very interesting diagnostic tool if you want to know a particular phase in your seismogram, and you don't know what the sensitivity of that phase or what part of the model contribute to that phase. Well, the kernels would actually tell you any part of the model that would actually have a scattered arrival at that window. So that will help you understand the phases, unknown phases better. So this is what I promised, this technical issue of time convolution of forward field and adjoint field. How do I make sure for any time instance t, I have access to time t instance of the forward field and t minus t instance of the adjoint field? Well, there are actually a couple of solutions. One is called storage solution. I call it storage solution because what you do is say, well, I cannot, if I carry forward field and adjoint field simultaneously in memory, I can only get time t instance at any given time. So what I need to do is I need to compute the forward field, and I save it as a function of time and space. So t sxt for all time instances. And when I compute the adjoint field, I just pick whatever time slice I need from the forward field to do this calculation. So that's two simulations, one forward, one adjoint, but there's a lot of storage and IO cost related to saving the forward field and then reading it back and forth. Subsampling compression helps, so that there are schemes out there, but SPECFEM uses the so-called CPU solution. So instead of storing field, we're actually recomputing the field. So we run the forward fields, and you'll see later in your tutorial, you save the forward wave fields only at selected time steps. So this is a checkpointing idea. And then when you back reconstruct the forward wave fields with periodic resetting during the adjoint simulation. So in other words, you compute the forward field, but you save some time instances, and then you go back while you carry the adjoint field, you go back and reconstruct it, the forward one, so that at any time instance of t, let's say your forward field run to t, sorry, adjoint field run to t, and then your back reconstructed forward field will be also running over to here, and then there will be the right time instances for you to compute that time convolution. And this is particularly important when you have attenuation present. Now for elastic wave field, it turned out it's even easier. We don't even need to do checkpointing. We only need a checkpoint at the very end for the forward field. With the wave field at the last time frame, you can just reconstruct the entire forward field because there's no attenuation. And reconstruction is completely accurate. And then you can go through the same idea, except of course, compared to the storage solution, you have to have 3 simulations, 1 forward calculation, and you save the last time frame, and then you go back to reconstruct the forward field while also carrying in memory the adjoint field. So there's the basic so-called kernel simulation step. You actually have 2 fields carried simultaneously in memory. So you'll see this in Akash's tutorial. So what you start is first step, you run a forward simulation. You set the simulation type to be 1, which is forward, and you save forward to be true, which gives you a chance to save the last time frame, and which you can use later for reconstruction. Then you select the phase and measurements that you need, and then compute the corresponding adjoint sources. And there's scripts to do it for simple travel time measurements. But if you have your own designed misfit function, you just have to come up with a way to write down the expression for your adjoint source, and you can implement it with a small code. After that, you write the adjoint source files. You can launch the kernel simulation. You set the simulation type to be 3, which is adjoint. You might wonder what 2 does. I mean, it has to do with source inversion, which we're not going to cover here. And then you also, when you said you don't need to save any forward in this case. Once you get the kernels, you might want to visualize it. Paraview is one of the tools we've used, but there are other visualization tools out there. For the next step of full waveform inversion, sometimes you also want to smooth the kernel, because the kernels will have regions where, just because the limitation of point source approximations will have pretty large values, you want to smooth out the kernel to get rid of those really kind of what we think of as artifacts around the source region. And that's basically an implicit regularization. So instead of adding a regularization term in your misfit function, you kind of smooth the kernel and use it as a kind of implicit regularization. And it can be quite costly. So because depending on the size of your Gaussian cap, it might require a lot of calculations. So one of the things we're working on in our group here is to figure out how we can use a PDE-based smoothing and make it a lot more affordable. So the next step will be tomorrow, for the full waveform inversion, how do you search for an optimal search direction once you know the gradient, and how do you actually update the model from that point on. I think I am done, so I'm going to pass it over to Carl and Akash. Thank you.
Thank you.
Oh, sorry, just one slide. I forgot that's just the advertisement for the in-person workshop for developers and users in University of Toronto, coming up in the end of October, which is right before the SSA tomography conference. I don't think we have room for in-person, but we will be offering virtual attendance. So if anybody is interested, I think you can still sign up for virtual attendance. And we would love to have some of your blood to come in and help us now continue to test the code, develop the code, and contribute your own idea to the future direction of the code. So thank you very much.
Thank you, Chinya. Zoom clapping. That's a great start for our day. As she's also alluding and sort of foreshadowing what's happening tomorrow. But today, the natural thing is to think about these sensitivity kernels because they're the building block for the imaging problem. So is anyone, let's take a couple questions. I know we're a little off schedule. It doesn't matter. We want to still have time for you to interact and ask someone like Chinya directly. If you have questions, there's some things in the chat. But for now, I want to encourage people to talk since we're here. And yeah, Jordan, go ahead.
Thank you. I really enjoyed seeing your connection between the adjoint expression for the misfit and the travel time misfit expression. Can you, I haven't worked through that myself, but do you get can you recover the ray-based expression by inserting the asymptotics into the full wave expression?
Yeah, let me go back and share this. So, I mean, that's exactly right. So I was trying to emphasize that and saying that, we're not the one who's inventing this whole concept. Find the right slides. Okay, so maybe I think it's later here. So yeah, so if you had inserted here the S and S stagger, these are basic just wave fields, right? If you have inserted as a asymptotic ray theory, which is what they did in the Dallin 2000 paper, then you get banana donut kernels. And if you had inserted with normal mode solutions, you would get kernels that are very similar, but still a bit different. Just because it's normal mode solution, it's still you're going to have cutoff, so you're going to have some rainings. If you had used a surface wave expression, asymptotic expression for S and S dagger, you're going to get a surface wave kernel, and it'll be mostly just on the surface with some depth sensitivity. So yeah, so these expressions are actually universal, of course, under the framework of single scatter approximation, right, or Born approximation, and you can produce your own, synthetic expression, analytical or numerical, and put it in here, and they will give you kernels. I don't know if that answers your question.
Yes, it does. Thank you.
Sure.
Other questions, or if you had one in chat you wanted to throw out there. Well, we'll keep going.
I had a question.
Yeah. Oh, sorry, there's two. Thank you. Three. Yay. Can you pronounce your name for everyone?
Kieran.
Kieran, great. Go ahead.
I think maybe I kind of know the answer to this question, but these sensitivity kernels they look like they're calculated with a correct model. And I guess my question is, if you're starting an inversion, like in your first iteration, assuming your model will not be correct. So I guess I'm just kind of wondering what the interpretation of a sensitivity kernel is if your model is wrong.
So that's a very, very good question. So sensitivity kernels, they are, I mean, these are basically they're derivatives of Fichet kernels, derivatives of whether it's a misfit or a measurement with respect to model based on a particular choice of model. So it could be the current model or initial model. And actually, every time when you go through this waveform inversion process, at every step, you're at a different model, and you have to compute the gradient at that point. So that kernel you computed is only for that initial model or reference model or some model in the iteration process. So we wouldn't be able to know what the true sensitivity kernel is for the true model because we don't really know the true model is, right? The hope is that by using the gradients, we will be able to approach the minimal solution or the optimal model, and then by then the kernels will be hopefully closer to the true sensitivity.
Okay, thank you.
Sure.
Go ahead, Roby.
Yes, great talk. I have two questions actually, but the first one is, can you clarify why when you show the K alpha, we didn't say anything? Is there a particular reason for that? Maybe I didn't get it.
Sorry, which one?
Which one? K alpha. So when you show the K alpha, you said that you cannot see the donut shape for the K alpha. and I didn't really understand.
Are you talking about this slide?
Yeah.
Okay. So you're
So the K alpha.
Oh, right, yeah.
This
Yeah,
one.
so, yes. Yeah, sorry, I should have explained this more clear. So this is the S kernel, right? So that's for SH wave. You're picking out the S phase, and you want to understand where are the parts of the model that would would scatter the incoming field and then generate scatter waves arriving at the window that's similar to this S phase. And of course, it's an S wave, right? So I mean, conceptually, it should be mostly sensitive only to the S wave model. So alpha is not as sensitive. But it's interesting that if you compute it in terms of density, kappa nu, there's a pretty strong density sensitivity, but it doesn't mean that it's necessarily going to give you a lot of information about density. It's just because these two are kind of canceling out each other.
Okay.
So yeah, so that's why it's important to use the right parameterization depending on what measurements you're making.
Okay. Yeah. And a quick follow-up. This is more general. So, so technically, can we use this adjoint tomography, this adjoint methodology if you have local data, for example? So in a way similar to local effect tomography. I'm just wondering if it's possible.
I don't think the technique itself is limited to the scale. I mean, waveform inversion has been used in industry quite prevalently in the past decade too. Okay. And you can go from kilometer scale to our problems, which local scale is 200, 300 kilometers to continental scale or the globe. Okay. I think the only difference would be what the full solver would be, right? You want to use a solver that's proper for your region and accurate also.
Okay. All right, thank you.
Sure.
Go ahead, Luis.
Hello, very nice talk. Thank you for this very clear explanation on the kernels. I have a few questions. The first one is related to when you compare the scattering integral method with the adjoint method. I know that the paper by Po Chen back in 2007 discussed when to use one and when to use the other one. So the way I understand it is that the physics are the same, the formulation is almost the same, but the only that changes is that the order of operations or the order of the convolutions that you do. Is that correct? Or like in your what are the main differences?
My understanding is that it's really a choice of whether to compute the individual kernels or not. Like I said, there are advantages of computing individual kernels. In some sense, when you have the access to individual kernels, like maybe Brian will mention this, it's as if you have not only first order gradient. So here we're talking about, compute the first order gradient of the misfit or measurement or misfit measurements. But it's also, you also have access to the second order, at least approximate second order derivative of the misfit. So what that allows you to do is to do quasi-Newton, like what you mentioned yesterday. You can do quasi-Newton type of inversion, and it is also the advantage, right? If you have the full matrix, I mean, if you can afford it, you can do SVD, and you can do. I don't think people do it. It's probably too big to do it. I'm just saying having access to that G matrix is definitely beneficial for, like checkerboard tests and stuff, right? But of course, but I think in that case, in order to get the individual kernels, you do have to store wave field, even if you smartly use social receiver reciprocity to save the field by injecting this three component unit forces at the receiver. That's still a lot of storage, and depending on the size of the problem, it may or may not be tractable. So that's why, I mean, for us, we chose to go the route of adjoint state methods. And I think what you mentioned yesterday was also important, that now, with the computational cost being a lot less compared to the past, it's probably going to be fast enough, even though we don't have access to the full G matrix, that with enough number of iterations, we can still get there. I mean, the other thing you have to realize for the scatter integral method is, yes, they're computing individual kernels, but it's only for a 3D model, just like an early question mentioned, right? It's only for one 3D model, current 3D model. If you have iterated, if you have solved this system, let's say, get a new model. In principle, you need to recompute all the kernels. So that means restoring all the fields for all the receivers. And depending on how many times you carry that, there is a balance between storage versus computation there between the two methods. I think there's a use for both, absolutely out there.
Okay, and sorry, I have another kind of different question. So I guess you mentioned how to compute the issues related to the amplitude of the kernels. How do you make sure that the absolute amplitude for those kernels are like the correct amplitude? So you said that you needed to normalize the adjoint source or something like that?
I mean, a couple of places. So for example, when you look at the travel time, are you talking about the travel time kernels? Well, in this case, yeah, you do have a normalization there, just to basically to link the travel time with the variation of the synthetics properly. I mean, the other, I don't know, are you referring also to the regularization? So if the kernels coming out of the calculations, because we use because the numerical solver assumes point source, right? So putting a point force here, let's say, or a moment tensor. The field is not, even the SPECFEM method, the field is not really accurate, right there at that point. Because I mean, when you think about it, it's a singularity, so it's not quite right there. So when you compute the kernels, that the values at those points tend to be artificially large, and you need to smooth it in order for you to get, and you'll see, I don't know if you have experience running these kernels, if you get the kernels out directly from the computation and you just plot it without knowing what the right color bar to choose, usually you won't see anything other than 2 dots at the source and receiver. That's just because those artificially high values that swamp the whole color bar. But if you lower the color bar or shrink the min max, and you will be able to get the values, and that's why it's important to regularize it before or smooth it before we go to the next step.
Okay, thank you so much.
Sure.
Go ahead, Siri.
Hi, yeah, this is Carrie Nunn. So I have a question. I'm really interested in looking at the moon, and I wondered if it's possible to use any of these techniques in such a strongly scattering medium. I kind of assumed that it wouldn't really be possible to try to do inverse calculations, but I'm just interested in people's opinion about how possible that might be.
Yeah, that's a very interesting question. I mean, if you recall, I mentioned quite a few times, there's a single scatter approximation, right? We're using Born approximation. So we're certainly not taking consideration of multiple scatters, at least in the kernels itself. So I would say for the moon case, if you have a lot of scatters, it might be difficult to or these kernels may not be the best way of imaging. But on the other hand, if it's not, I mean, it depends on how much scatter there is and what scattering regime you're in. It is well known that this Waveform Inversion method, even though the kernels don't necessarily reflect the multiple scatters, but if you iterate it enough number of times, the multiple scatter effects would still be captured, just because the forward physics itself has the multiple scattering in it. So I don't know if I'm answering your question, but yeah. So I would say it really depends on the scatter regime you're looking at. It might be difficult. I mean, if you want to do an imaging problem, probably it will be difficult if you have a lot of scatter waves. And if you look at these examples, we're working with very clear pulses that where the kernels are pretty much from rays that we know. If you've got pulses that are from multiple scatters, it will be difficult to compute the correct kernel.
Yeah, I mean, I'd assumed it was so difficult it was impossible. So I'm interested that you you think if you do it enough times, you might get something interesting out.
I think it depends on what your starting solution is. I don't want to discount the FWA when you have multiple scatters, because it can handle multiple scatters if you have enough number of iterations and if the solver is good. but I really don't know what the right answer in that case is. I mean, you can of course give it a try.
Carrie, could I ask something, Chinya? Is there some reason to think that the moon is more complicated or heterogeneous than the Earth? I thought the opposite.
Well, I know what. Yeah, sorry. Go ahead.
Yeah. So what we think we know so far is that it's very strongly scattering. So it just behaves differently to the Earth. So it's not necessarily that it's more heterogeneous, but it has a lot of scattering within it, and it's very low attenuation. So any scatter does, like it you can, your signals will last for hours rather than minutes.
Interesting. Certainly the lack of data seems to be the biggest problem to doing imaging compared to the Earth, but I guess that's also overcomable with technology eventually. All right, great. Any other questions? There was one that dropped out there, but I think we'll say let's just keep moving, and really great to see some engagement there. And we'll thank Chinya one last time with a Zoom clap reaction there. Let's take a 5-minute break, and then Akash will get us back going. So let's just everyone stand up, stretch, or whatever, and we'll see you in 5 minutes. Thank you. All right. Akash, could we do a sound check here? Just make sure.
Yes.
Right.
Can you hear me?
Very good. Yeah.
And do you see the notebook?
Yeah.
Okay.
I always find that, yeah, the computer audio seems very good.
Yeah.
External microphones. I don't know. I guess that makes sense.
Sometimes. Yeah.
Let's just wait a second here, but kind of call people back. We've got a really great number of people still here, which is good. Okay, well, I'll just sort of semi-introduce the next stage here, but we welcome back, or as you come back, we are going on to the technical part. And originally, we wanted to introduce SPECFEM 3D. It's compiled. You have it at your fingertips. And so we want to at least have users leave the workshop saying, ran SPECFEM 3D, MPI, and, you know, understand the basics of this. And so we were going to run that yesterday, but we ran out of time. So we're going to do that here, which sets us up well to return to this, hopefully at the end of today, where Akash will kind of highlight the example of making these kernels, or featuring the kernels that were made and shown in the Lewin-Trump 2006 paper. So I'm going to hand off here. And Akash, realistically, we may have to cut one of the two extra examples. So think about what you might sacrifice just in the interest of keeping things moving. Go for it.
Okay. Yeah. So hi, everyone. I am Akash Gupta. I am a PhD student at the University of Alaska Fairbanks, and I'm working with Professor Carl Tape. So today I was going to talk about SPECFEM 3D Cartesian specifically. So we were supposed to go through this yesterday, but we couldn't do that. So now I'll try to give a slight introduction to SPECFEM 3D before moving on to the kernels. So we kind of take a step back, and then at the end, we'll be seeing the kernel examples that Jinya was talking about. And I can show you like how to implement that in SPECFEM 3D. So we'll get started with SPECFEM 3D. And before that, I'll just make two quick points. So one is yesterday, we had a lot of questions in the chat regarding SPECFEM. So during this demonstration of SPECFEM 3D, we'll assume that you're asking questions regarding SPECFEM 3D Cartesian. But if you have questions regarding SPECFEM 2D or SPECFEM 3D Globe in specific, it's better that you mention that within your chat questions.
Akash, I just realized something. Don't we want to make sure people have like launched and opened the container? Let me just ask.
Yeah.
I don't think we've stepped through this.
Okay.
Well, here, I'll just launch a question and say, do you have this open on your own computer? Do you have this notebook, and have you launched the container? So please respond to that. Probably not. So we'll have to sort of walk through this, but I just want to see in the case that everyone's already there. So please answer this poll question, meaning like, have you opened the container? Are you looking at things?
Carl, one quick note. It seems that the container that I'm looking at is slightly different compared to the one. So the D1C, the first page of mine is slightly different compared to what it's showing. I'm just wondering if that's normal.
That should not be normal. It's possible there's a would there be any clone check, Bryant or Akash?
Yeah, you might have to. We might have to go through a Git pull to make sure everybody's on the same.
Then let's do that. We've got. You guys can see the poll. Someone can see. We've got about 10 out of 90 people who are saying no, we're almost ready. But some people may not have done the Git clone. So, who wants to do that, Bryant or Akash?
Yeah, I can go through that.
Okay.
I can go through that quickly. Yeah. So once you start your notebook, after doing the Docker run command in your terminal, you see this.
Wait a minute. We want to do the Docker run command in the terminal because some people don't have the. Let's start from scratch here.
Yeah. So once that is done, we can do the Git pull. Yeah.
But can you demonstrate? Open the terminal and
Docker run.
Yeah.
In that case, I'll have to close my notebook and all the setup.
I can do it.
So probably, Brian, that would be better. Yeah.
Okay, give me 1 second.
I realize, you know, just please be patient. There's also people not responding to the poll, and it's possible that they, you know, would like to catch up on this stage.
Yep, sorry, let me just clear my screen a little bit and get back to this kind of clean slate. So again, kind of starting from yesterday, we're in this empty working directory, and I'm also looking at this README that's on GitHub. So this is just for people to get back into their containers. We're scrolling down all the way to the bottom of this Edge Docs README. We're looking at workshops day 1 through 3 startup procedure. And again, if you ran these commands yesterday, all we really need is this Docker run command, and there's different instructions for your different operating systems. So I'm on a Mac Intel chip, and I'm just copying this Docker run, making sure that I'm in my working directory that I was looking at yesterday. So just copy this, paste. And if you enter, you should be getting some display messages that are telling you that you're starting up your Jupyter notebook, and it's going to give you that web address again. And so I want to copy that, put that in my web browser. And so here again, we're starting a new container. So if you're following my instructions here, the kind of steps that we did yesterday, we need to redo. So we're going to have to do another git pull on Edge Docs just to make sure that we have the freshest, kind of latest workshop material. So make that bigger. Zoom that in. And so to do that, again, we're going to hit this terminal button down at the bottom. And there's some commands at the bottom of this document that's just cd edge docs git pull. That'll get us all to the latest workshop material, and hopefully everybody's on the same page. All right, so you should be seeing this.
And if you have any sort of merge error that Git often delivers, there's fixes for that. Maybe speak up if you have an error at this stage.
It works now for me. So yeah, the git pull works. So.
Cool.
Great. Cool. So I think, yeah, we're on the same page now. I think I can hand that off to Akash.
Okay.
Find my Zoom stuff.
We have someone in the chat asking to go to a break room.
Yeah, I can help them out.
You're
muted, Carl.
Yeah, anyone that's not at the stage or doesn't have the container working or any kind of error, just head to the break room and someone will find you there.
Carl, you want to do a poll or do I start?
Sure, let's do a quick poll. We'll relaunch, and that'll give us an idea of how many might be going to the break room. So just, are you ready to move on? Do you have the day 1C notebook in front of you on your own computer? Okay, so maybe 2 people. Yeah, just head to the break room and we'll help.
Free to join breakout room 1, and we can send a host in there to help you.
Well, that means I need to make the breakout. Sorry.
You did.
Did I? Okay.
Or somebody did.
Good, great.
Okay, so do I start, Carl, or do I?
Yeah, go for it.
Okay, so seems like most of you are ready with this notebook, day 1C. So yeah, so I wanted to make 2 points. I made one, like keep your questions, like SPECFEM questions. We'll assume you are asking questions about SPECFEM 3D. But if you have questions about the other packages, please mention those package names specifically when you ask the questions in chat. And the other main point I wanted to make was when you run these cells today, run them sequentially, because if you don't run them sequentially, there might be some path error and you might break something, and then like we might need more breakout room time. So yeah, I don't know whether I should cover the Jupyter Notebook instructions again. Probably I'll go through that quickly. So if you click on this top
I think you
arrow,
can skip that, Akash. We're
okay.
Yeah, we're
I think
pros by now.
everyone's pretty comfortable with that. Okay. Yeah, so basically SPECFEM 3D, a lot of it would be similar to SPECFEM 2D directory structure and how to run it, but there are some differences. And then, yeah, any subsequent use of the term SPECFEM 3D will refer to SPECFEM 3D Cartesian. That's what we'll be looking at. The best reference is definitely the manual. Like, it's very detailed and it deals with very specific cases as well, which might not be covered today. And then SPECFEM 3D is already installed in your container. So we don't have to worry about the installation part today. And yeah, let's get started. Okay. So first we'll explore the package. So some of this will be very similar to SPECFEM 2D. So I'll just run through that. So let's run the first cell. We import some Python packages, which we'll be needing later. And then let's go to the SPECFEM 3D directory, which comes with the container, and see what's inside there. So here, if you see, we have quite a few folders and files, and it might seem confusing at first sight of like what all these are. So all these might not be the most relevant in the beginning when you are starting to use this package. So what I found the most useful or like the most relevant were these. So you have these folders and files among this. So we'll be looking at these 5 folders. So the bin folder, so Brant already talked about this. It has all the executables, like the compiled code, Fortran code. So the main 3 executables that we need for a basic simulation are these. Let's look at, let's run this cell and see. Yeah, so you have all these compiled executables, but we don't need all these at the moment, but SPECFEM does have quite a few of these. So the basic ones would be XMeshFEM 3D, which is your mesher code. It creates the mesh for you, internal mesh. And then you have the generate databases, executable. So what happens here is your model parameters get assigned to those mesh nodes that you did in the first step. And then finally, you solve the wave equation using the solver, which is called XSpecFem 3D. Then the data directory, this is where all your input resides. So yesterday also you saw something like this. So here you have the source definition in the CMT solution and force solution files. You have the mesh definition in MEshFEM 3D files, which is your for internal measure. Then the model is defined through MEshFEM 3D files. And there is another way you can use tomographic models using this tomo files folder. And then your station definition is defined in the stations file. So yeah, let's move to this cell, the output files folder. So output files folder has basically the output. So it will have the output seismograms and the log files, as well as the databases folder if it is inside output files, where you will have the mesh database files as well as your generated database like the model files. So yeah, that's the output files folder. So these are the 3 main folders for running a simulation. Then there's the source directory. Here you have all the source code. So like the source code for XMeshFEM 3D can be found in MEshFEM 3D folder. Generate databases has the XMeshFEM 3D related codes, and then the solver is here, SPECFEM 3D. Then there are some other codes as well. So if you are looking to add your own features or modify something, then these are the directories you want to go to and find that specific code and write your own Fortran code. And then, yeah, and if you think it's useful to the community, and you can make a pull request, and then it will be reviewed and integrated to the package. So yeah, and finally, I wanted to discuss this examples folder. So here you have quite a few examples, which are very useful in getting started. So first point I want to mention here is these examples have README files, and they will instruct you, like take you step by step through how to run these examples. But again, like the manual, I would say is the best reference. It has all the details and the specifics of what to do and what not to do and how to run. These are just like in the README files, you will get the steps, but some detail and specifics you will only get in the manual. So out of these examples that you have, the 3 more common ones, I would say, like the good ones to start with would be these, the homogeneous half space example, which again has a variety of examples within it. And then the MEshFEM 3D examples has 1D layered models, while homogeneous half space is just homogeneous half space. And then another example which was recently added is the sensitivity kernels from the Liu and Trom 2006 paper example. So you have this README file, and it will guide you through all these examples when you go to these specific folders in the examples folder. So we'll be looking at the sensitivity kernels example toward the end of the day if we have enough time today. And then right now we'll start with the homogeneous half space example and then build towards a 1D model. So yeah, so let's now move on to this. Setting up our simulation for the first homogeneous half space example. So as we did this yesterday as well, so we will have a separate SPECFEM directory, and there we'll link the executables that we already have compiled for you. Then we'll have an output files folder so that all the output gets there. And then we'll copy the data folder for the specific example we want to run. So all this goes to the SPECFEM work directory. So let's run this cell. So what we are doing here is, okay, just a second. I don't think this problem would have occurred with you, but I need to sort something out very quickly. So I already have some files here, and I should remove it because I ran the example earlier. So this should work now, I hope. Yes. So let me run this once again. Yeah, so it looks to be working. So basically, we just created a SPECFEM work directory. We went into the SPECFEM work directory, we linked the executables, and then we created an output files folder. We are yet to copy the data folder, which we'll do in the next section, in the simulation section, where we'll copy the data folder specific to the example we are interested in. So, okay, I want to pause for like 30 seconds and ask, like, was everyone able to follow till now before we start the examples? Or like, are there any questions? Or
you mean
I'll throw a poll out there here. Are you ready to move on? Which is kind of just a generic as it sounds. Oh yeah, feel free to just ask a question. Try to gauge whether we go too slow or too fast. Okay, yes, move on.
Okay,
everyone.
So that sounds promising. Okay. So basically a SPECFEM 3D Cartesian simulation involves 3 steps. You do the meshing, you generate the mesh, you discretize your domain into finite elements. Then you do the database generation where you are assigning the model parameters to those mesh elements, and then you solve the wave equation. So there are like 3 distinct steps. So let's copy the data folder, which we did not do. So we'll run this cell. And yeah, so we copy the data folder from this homogeneous half space example. So we discuss this examples folder and we go to this homogeneous half space example and then take the data folder from there and paste it into our SPECFEM working directory. But we don't have the internal mesh files within the data folder. So we had to copy that separately. So now we have the mesh definition also. So if you look at the data folder now, you have all what you saw earlier, and you also have the MESHFEM 3D files, which define your mesh and the model as well in this case. So let's explore the MESHFEM 3D files. So here you have the mesh par file, which is the mesh parameter file. So we look into the mesh parameter file, and then we have this interface file and the interfaces file. So suppose if you have a 4-layered model, you will have 4 interfaces. And we ignore the bottommost interface. We consider the ones above. So the interfaces file has a log of where the what interface file we are using to define those interfaces. And then the interface file for each of those interfaces has the depth and like the values of where that interface lies. So we won't be discussing much about interfaces and like the file specifically, but we'll look at the mesh par file. So we'll run the next cell. So this is your whole mesh par file. It defines the domain, like the latitude, basically the X extent and the Y extent, the depth of the block. And then the other important things will be what is the name of the interfaces file from where it can fetch the information about interfaces, how many elements you have in the xi and the eta direction, which in this case would be the x and the y direction. And then how many processors you want to break your whole domain into. So here we'll have 4 slices, like 2 into 2, 4. So we'll break the whole domain into 4 slices. So one processor will deal with 1 slice each. And then the other thing.
I'll just pause. I'm just going to sometimes slow things down, but just to put it in perspective, this would be a 2x2 simulation, but the same code, you know, has been run with, I believe, over 1 million processors. So just to kind of, we're looking at very small scale problems that are still MPI, but it's worth kind of emphasizing that the same code is being used at pretty phenomenal scale, even to benchmark some of the hardware that's being developed. Go ahead, Akash.
Okay, yeah. So yeah, the other thing would be, yeah, this point, number of materials. So here, since it's a homogeneous half space example, we have 1 material for the whole half space. And you have the material ID, which is 1, density, VP, VS, then Q kappa, Q mu, but we won't be running attenuation. It won't be on during our simulation. It's just there in the definition. Then this 0 corresponds to the anisotropy flag, and 0 means no anisotropy. And then 2 is the domain ID, which means it's an elastic domain, and acoustic domain would be 1. And then the last part of the mesh par file has this regions, like basically how many elements you want in the X and Y directions, xi and eta directions, and then in the vertical direction, and what material you want to assign to that region. So this material ID1 means this one material ID1 will get assigned to this region. So that's more or less the mesh par file. And then the next step would be to run this executable XMeshFrame 3D, which will read this mesh par file and the interfaces file. And here you see, like, we'll run it using MPI on 4 processors, and it will create our mesh and store our mesh details in this output files databases MPI folder. So yeah, so here, so we had a blank databases folder, but now we have all these files. So you'll see proc 0, proc 1, proc 2, proc 3, basically corresponding to 4 processors, because we are using 4 cores for this. And then you have this database and the mesh.vtk and skewness.vtk files. So VTK files are basically the visualization toolkit files you can use to view our mesh on ParaView or some other software. And the database file has the information about the mesh. So quickly moving on to the generate databases step. So here your model values based on this model definition we have in our mesh par file will get assigned to this region. And so let's run the generate databases executable similarly, and then again look at the databases folder. So we'll see a bunch of new files coming in for each of these 4 processors, and we'll have a vp.bin, vs.bin, and those binary files, which will have information about the VP model, VS model, row model. And if you have attenuation, it might also have those files as well. So yeah, they should not take a lot of time. It should take like 15-20 seconds, I hope.
I like how, Akash, you were kind of emphasizing this mesh making has, in some sense, nothing to do with the model that you're assigning values to, VPVS. But on the other hand, we design the mesh based on an understanding of what values are going to be assigned. So this is where it kind of is back and forth. But geometrically speaking, the mesh is the mesh. It knows nothing about, you know, it's got topography, but it knows nothing about the values that are about to be assigned. And so that's the second step he's showing is all about that.
Okay, so this seems to be taking a lot more than I expect, like the time, but let's see. Maybe I'll just keep talking while that cell runs. So
can I just make a quick point too, Akash, that we saw in SPECFEM 2D that we don't have this generate databases step. And this actually just happens directly, I'm pretty sure, in the solver step of SPECFEM 2D. So it mixes those 2 steps together. So just, yeah, keep that in mind if you're, for the examples that we run in 2D, when you try to port over to 3D, there's an extra step here.
And I also believe in SPECFEM 3D Globe also, you don't have that extra step. I think so. So yeah, so this is specific to SPECFEM 3D Cartesian, and yeah, this generate databases has run. So now you see all these vp.bin, vs.bin, all these files, qkappa.bin. So now you have your models also assigned to the mesh. And then, yeah, so now let's look at the mesh and the model. Like, what does our homogeneous half space look like? So here you see we have a domain, and the horizontal extent along the x and y direction is 134 kilometers each, and the depth is 60 kilometers. All this is in the mesh par file, all the details. And as we saw, like, we had 36 elements along the two horizontal directions and 16 elements on the vertical direction. So if you count this, it's exactly 36, 36, and 16. And now this whole big cuboid is going to be broken into 4 equal slices and sent to each, like, 4 cores, because that's how we designed our simulation. And if you look at so this is basically the VP model. So here we have a VP value of 2.8 kilometers per second. You can also plot the VS model, or you can just plot the mesh if you want without any models. So that's just the overview of the simulation domain that we have. And now let's move on to the final step, which is solving the wave equation. So I'll ask you to run, okay, let's look at the CMT solution file. So this is a standard centroid moment tensor format of this file, where you have like different earthquakes from the earthquake catalog. You have time shift, half duration, dealing with your source time function, those kind of things. But mainly let's focus on just the location, which will be your latitude would be your Y coordinate, longitude will be your X coordinate, and depth will be your Z coordinate. And then you have these 6 moment tensor coordinates corresponding to a earthquake, which I believe here is a fictitious earthquake. So yeah, that's your CMT. You can read more about the CMT solution. I've linked it, the paper where the CMT solution is talked about. The stations file. So basically you have the station name, network, then you have I believe this is the latitude, and then this is the longitude, and then you have the burial and depth. So let's plot the source receiver geometry to have an idea of what we are doing. So I just cut the simulation domain in half. So the Y dimension has been cut into half, and we have the source at the center. And then we have stations, equidistant stations along the surface, along this slice. And rest is pretty much same, the model and the mesh. So just to have an idea of what we are looking at. So I guess X50 is this station closest to the source, and X20 is the one farthest from the source. Yeah, this 22,000. So it's farthest from the source, and this 58,000 close to the source. But the source is right at the center, 67,000. So, okay, so now let's look at the par file, which is your simulation, like for the solver, this is your parameter file. So you can select the simulation type. For a forward simulation, it's supposed to be 1. And then for adjoint simulations, 2. And then if you want to do both together, you will do 3. If you want to save the forward wave field, you can set this flag to true. And then let's look at the n proc is the number of processors. So for our case, it's 4. N step is number of time steps, and dt is your time step, 0.05 seconds. So 5,000 to 0.05 would be 250 seconds. So we'll have a 250 second long simulation. And then let's look at another. So there's not the whole par file. It's just a section, top 30 lines of the par file. And then I'll show you another important segment of the par file. So here you define your model. By default, if you use this kind of a model or a layered model, which you are defining using a mesh par file, model would generally be default. But if you want to use one of the inbuilt models like 1D Prem, you can change this. And if you have an isotropic model, you can set this to an ISO, and then the anisotropic simulation capabilities will get switched on. If you have a tomographic model, you will have to provide a tomo path, but generally we save the tomography files in this folder, so you don't have to change this path. And yeah, this section, you define what you have in your model. So even though we have attenuation in our model, we have it as false because we don't want it in this simulation. So similarly, for anisotropy, you want to set this to true, and then there are other flags as well for other options. So let's run the solver. I should have told you to do this earlier because this is going to take like 5 minutes. So yeah, so that's the most computationally expensive step, the solver. And yeah, we'll wait for it to run before we run the next cell, else we'll get an error message. And yeah, maybe I can take some questions, or if you have any questions, the others also who can answer.
Well,
my computer, by the way, is still running generate databases. So potentially others are slow.
Okay.
Akash, will this generate timestamps as it runs, the LS?
Yeah, true. Yeah, so I can talk about that. Good point. Yeah, so basically, how do you track the progress of your solver? So you can, so you have this output solver.txt log file. So I don't want you to, I'll show you the files, but I don't want you to navigate necessarily. So let's go to the work folder. We'll go to the SPECFEM 3D work directory. I'll open the output files folder. So here a lot of dynamic things will happen as you run these executables. So right now we are running the solver. So here we have a bunch of these files like output meshframe 3d.txt. This is the log file for your meshframe 3D step. It tells you the mesh details, element and element sizes and all that. And then you have the output generate databases.txt. So this is the log file for the generating databases step. And now we are interested in the output solver.txt. So you'll see here in the beginning, you will have how many elements and those details, and then where your stations are, the source is. So location of receivers. So station 1, station 2, we have 4 stations. So we have 4 stations here also. Then we move on to this part. And then, yeah, so time loop. So here you see the time steps. So here it says total simulated time 250 seconds that we discussed. So yeah, it starts like this and time step 500. So as it goes further, you will have more time steps. So you can set up a value in the par file where you can define at how many time steps you want this to be outputted. I don't know whether it's fixed for the output solver.txt file, but at least the seismograms can be dumped out at several time intervals if you want, even before the whole simulation completes. So here we'll see a time steps every 500, after every 500 time step. So once 1000 time steps are completed, we'll see one more like 2 blocks, 2 paragraphs here, and then it goes on till 5000, and then you know my simulation ended. So I'm expecting this file to get updated on the fly.
It is, but you just have to reload.
You have to close and open.
I see. Okay, yeah. So basically, you have to reload it. Or another good way would be to go to the terminal. I don't want you to do all this, but I'll just show you. You can do a tail -f command, and then output solver.txt. And yeah, this will be like, you don't have to, yeah, it will just keep showing up. So the moment it reaches to 5000, and then it will show you end of simulation, you know your solver has run, and you can go to your output files folder and look at the seismograms and those things. So yeah,
you also mentioned the timestamp files that are being created.
Yes. So yeah, if you notice here, you have all these timestamp files. You don't necessarily have to open the log file. So here you'll see like timestamps popping up as the solver progresses. So yeah, let's see. We'll wait for, so half the simulation is done. So if any one of you have any questions while the simulation gets done, I think this would be a good time for that.
Somebody had a question about the difference between Cartesian and geographic coordinate systems. Carl had mentioned there's a flag in the par file.
Yes, so I basically skipped over that, but yeah, I can talk about that. You have a flag in the par file as well as the mesh par file. So your mesh can be in the geographic, like if your domain is in the geographic system, but you want to do a Cartesian simulation, you'll have to project your geographical extents to the Cartesian system. And then there is one more flag here for the solver as well. I forget why we have 2 flags, but yeah, we do have it in 2 places, and they both have their own utility. One in the mesh par file, but one in the par file as well.
You can actually use either one in either one. It's just to give total flexibility. You can, so it's not that they can override or have to be consistent, but in any case, this tells you that, you know, when you read in the stations file and the CMT solution file, don't expect lon lat, expect something else.
Yeah, so so for that you need this definition in the par file, and for your mesh, like the domain extent, for that you need this flag in the mesh par file as well. So you have it there as well. This where is this UTM projection zone, and whether you want to suppress the projection. So since here we are already in the UTM domain, we don't have any geographical coordinate defined stations and like domain. So we don't want UTM projection. So we'll suppress UTM projection, and that's why it's true. Let's see. Yeah, we are almost there. 2 more time steps. Any other questions? Maybe we can do one more by the time the solver ends.
I just wanted to point out that if you ran this, say, on a cluster, you know, it's comparable. Like the default SPECFEM example takes a few minutes, less than 5 minutes typically. So our run times aren't any different from a cluster. Of course, if you ran this on more cores, it'd be faster.
Okay, almost there. So yeah, next we'll be looking at the output files, and we'll have these SEMD files. So SEMD means displacement, but in the power file, you have flags for velocity and acceleration as well. And in that case, you will have .semv files. So now you see these files are here, the .semd. So let's run this next cell. If you have finished your simulation, for mine, it's done. So yeah, you have these SEMD files, which are the displacement files, but you might have SEMV or SEMA, depending on whether you had the velocity and acceleration flag on in the power file. So we'll look at one of these output seismograms. So the first column is basically your timestamp, the time, and the second column is your value of displacement. So the simulation here starts from -10 seconds. And since it's a 250-second long simulation, it will go to 240 seconds. And that's because you have this half duration for the source time function in your CMT solution file. And to incorporate that, SPECFEM by default has a buffer and it starts simulation so that you have that part of the simulation as well. So let's quickly look at these 4 seismograms at the 4 stations. We are looking at the vertical component. So you see the station closest to the source, X50, has a larger displacement, and then there's a static offset in the results. So basically, we read these ASCII files, the output seismograms, and plotted it using Python, not much here. So basically that's your homogeneous half space example. And before moving on to the next example, I'll remove the databases file from the output files directory because it's the largest sized component of the simulation. These files are very large, so I'll just remove it, and then we'll move all these files that we plotted, the source, the example, source receiver geometry, and the mesh files, to the output files folder and archive it so you can look at it later as well. And then we'll move to the 2-layered model. Okay, what happened here? I don't know what this. Anyway, let me have a look. I'm hoping it ran for everyone, but not for me. Okay. Did it run for any of you, like Bryant or anyone? This final step, I got an error message for some reason.
Sorry, I haven't run it, but what was your error message?
Yeah, it was like the output files folder not found.
It's probably some path related thing, you know.
Okay, I think the next step should work for the time being. I don't know what happened there. So yeah, let's quickly talk about this 2-layered model. I don't think we have much time, but yeah. So again, so most of this section is repetitive. Like you copy the pre-saved mesh par file for this 2-layered model. So it's already pre-saved for you in this additional material folder within the workshop folder. And then you go to the day 1C. You don't have to go there, but it's like already written here. So you copy this new set of mesh from 3D files while your source, station, and all the other definition stays the same. So we just moved the mesh from 3D files in the previous case from the data folder. I hope so. Let's have a look. Yes. I don't know. This might be tricky.
The question about the frequency content, just while we're going here, was kind of addressed in this last example, which I'm not sure we'll get to, but looking at what it would take to, say, resolve frequencies that are twice as high as the target ones. What are the costs for that? So it isn't an automatic, you don't just say, I want 4 frequency waves. Here's my model. What's my mesh? A little more hands-on. Go ahead, Akash.
Yeah, okay. I think this is working fine. I hope so. So yeah, so we just copied the meshframe 3D files into the data folder, and we had already moved the previous meshframe 3D file. So now we have the new mesh and the model, and the source and station stays the same. So now we'll just see what we changed for making a two-layered model out of a homogeneous model. So we'll just do a diff command on the.
Can I pause for a second and throw a poll out there? So even though Akash, you had this error, you're just moving on, right? It's okay.
Yes, I believe so. Because
okay, it sounds like some people, a lot of people did not have the error. Some people did, but at any rate, I'm just going to ask a poll question. Are you run the diff command here? Do you see the diff? That's the poll question right now. So let's see, relaunch poll. Go ahead. Do you see the correct diff? All right, go ahead, Akash. Everyone's there.
Okay, good. So yeah, so basically I'm trying to show what changes we made in the mesh par file to make a two-layered model out of a homogeneous half-space model. So out of that whole mesh par file, this section where you had materials, we increased the number of materials to 2. And then we have 2 model definitions for each of the layers instead of 1. So one thing to take note of here is generally in SPECFEM, we have this numbering starting from the bottom layer. So since the bottom layer is the high velocity layer, which we are trying to add. Okay, I realize I did not talk about this. So here what we do is we take the homogeneous half-space model. It's a 60 kilometer deep model. We take the bottom 45 kilometers and give it a higher velocity than the initial case we had. So this bottom layer, which is now the layer 1, because SPECFEM's numbering is from the bottom, has this higher rho value, higher VP value and VS value, while the second layer is the same as the previous example case. So it has the same parameters. So now we have 2 layers, and now we'll have 2 regions as well. So we don't change the mesh here, but we just change the model. So the mesh remains the same. So since it's broken into 15 and 45 kilometers, like 1:3 ratio. So we break the number of vertical elements in a similar, you have 12 elements in the bottom layer and 4 elements in the top layer. So basically your meshing doesn't change at all, but your model changes. So let's quickly go to the next step. We'll run the measure and the generate databases together. And then we'll look at the model. I think I can, let's wait for this to run. I don't want you to run the next cell, but I'll try for myself. Like if the model shows up, okay, it won't show up till that runs, but we could have discussed the model while it runs. So I'll talk while that happens. So basically here in the bottom 12 elements, which is the bottom 45 kilometers of this domain, you will have a velocity, VP velocity of 4 kilometers per second, while the top will stay blue and the mesh elements will look exactly the same. So yeah. So we'll see that once this runs. So I hope it's running for everyone.
So while we wait, let me ask a quick question. If you generate your mesh with Qubit, for example, do you still have to fill the mesh profile as well?
I'll pass that on to probably
no,
or someone.
You don't. The mesh par file is only for the internal mesher.
Okay, makes sense. Okay. Yeah. Oh, just a quick follow-up. So how do you, when you generate with Qubit, so how do you specify the surfaces that will be, for example, the surfaces that will have the absorbing boundaries of the surface? So where will those be defined?
Yeah, so basically, I did not go through that in detail, but if you look at the MeshFrame 3D files folder, which has the mesh par file, it also has these interfaces file.
Yeah, I saw that for the internal, but for if you do it with Qubit, if you do not have to do the mesh par file, so where would you define those parameters?
I'll have to pass that on to Carl or someone.
Sorry,
you have a it's called num velocity file. If you have an externally defined mesh with domains, you can either assign that domain a uniform value, or you can tell it to go interpolate from an external tomography file. So you can have complex subregions that are either getting assigned a value or coming from an external tomography. It's pretty flexible in that regard.
Okay.
Okay, I think this step is over for me, the mesh from 3D and generate databases. So this is the model I was talking about. Bottom 45 kilometers has this 4 kilometer kilometer per second VP velocity, while the top has 2.8. And then you might ask me the question, why do I see the third layer? So basically it's a plotting artifact. So I plotted this using ParaView. So you have a sharp boundary here, like the velocity below this layer is different and on the top it's different. But I think the way the VTK files store information, they just store one value at one particular point. So they cannot have both values corresponding to the top and the bottom layer. So basically this zone where you don't have these values defined, it basically provides a interpolated value, and that's why you see a transition. But in an ideal case, this fourth element layer would also be blue in color, signifying the lower velocity layer. So yeah, that's our mesh and the model. And now let's run the solver if your previous step ran. And this will take similar time compared to the previous solver run. And then you'll have seismograms, which will look slightly different because we added an interface. So you'll have some interactions at the interface. It will more or less be similar, but you will see some more wiggles because of that interface. And then, yeah, we'll move the file. So that's basically about how you go to a layered model from this. So, I'll have to wait. Or maybe what I can do is while the solver runs, I can just talk through the completed notebook I already have, so that we save some time as docs. Day 1C. Yeah. So I'll quickly move on to the third example. So here what I have is, yeah, so in the third model, what we do is, since we have a higher velocity, so there are these conditions which you take into account while designing your mesh. If you're higher velocity, you generally can use bigger mesh without losing on accuracy, stability, and like resolution, I guess. So yeah, so if you don't use these higher sized elements for higher velocity regions, you will be just wasting computational resources where you don't need to. So to gradually transition from smaller elements to larger elements, you need this kind of a transition, which is called doubling layers. If you don't have that transition, like you won't have that boundary interaction, and your finite element solver might fail if it's like, yeah. So it's designed in a way that you have things transitioning gradually. There is node-to-node interaction on both sides of the interface. So basically to do that, we have to make some more changes to the mesh par file, and rest all stays the same. The CMT solution and all that solver part stays the same. So if you do a diff here for the third example, if you diff between the mesh par file for the doubling layer mesh par file and the mesh par file we just used, you will see that first, the mesh is no longer regular, like the elements in the bottom layer are different from the top. So you use regular mesh, flag has to be set to false, and then we add one doubling layer. But if you have more layers and more velocity jumps, you might need more doubling layers. So in the initial case, we had 0 doubling layers. Now we have one doubling layer at the 6th element. And again, the counting starts from the bottom. So if you count from the bottom, 1, 2, 3, 4, 5, 6, that's where your doubling layer is. And the other thing you would notice, I have slightly changed the number of elements in the horizontal directions from 36 to 32. This happens because when you double the elements, it has to be a multiple of 8. Otherwise, you will lose out on some elements and you cannot double them properly. So this thing is mentioned in the manual as well as in the mesh par file. There is a note that whenever you are using irregular meshes, that your regular mesh flag is false, you need these elements to be a multiple of 8. So that's why I've made this slight change. Otherwise, like the seismograms won't change for such a small change in element size. And then the top layer still has 4 elements as you had in the previous models, but the bottom layer now has half the elements. So here, if you see in the second example, we had 12 elements in the bottom layer to not change the mesh elements, but here we have halved it because we use doubling. And then yeah, rest is pretty much the same. And then if you run the simulation with this, you will see it will take about 1/3 or 1/4 of the time of the simulation we are running right now, the second example. So yeah, those were the main points I wanted to make out of this notebook. And in the end, I think I discussed this. And then selecting mesh element dimensions is governed by several factors: frequencies of interest, velocity model, computational accuracy required, computational time available. The quality of mesh as described in the Komatish and Tromp 2002A paper is, so they have this description and proper detailing of how to choose your, assess your mesh quality. So you can see what the number of grid points per wavelength is. You can calculate that based on your frequency requirements and the velocity. And then the stability condition for the time integration. So what your time step should be. If you use very fine elements, you need a smaller DT, and details about that is in this paper. You can read that. So yeah, that was pretty much it about this notebook. And I think the solver is still running, but yeah, you can just probably wait for it, or like maybe we can have some questions right now, or I don't know.
Yeah, let's take some questions. I mean, Akash, I think this is great. I mean, judging by everyone's, when we ask if people are following along, everyone's there. I mean, no one's going to soak in every detail here, but the impression of like, you know, I want to emphasize things like the difference between a finite element and the grid points. Like these aren't the grid points, what you're looking at here, right? There's like 5 points or 125 points in each of these elements. So that's the kind of thing we want to be emphasizing. This is great demonstration to convey the impression of what we're what this code is about. Akash,
Yes.
are there quite, there's a lot of stuff going in the chat. You know, I kind of pertaining to like, if you have a certain model, what do you try? And I would just advise for practical purposes, number one, don't trust every recommendation that comes out of the text files. If it says recommended time step is this, you know, just take that with a grain of salt. You can find the time step that's stable, and then you want to make it as large as possible without breaking the simulation. And in many practical purposes, since you're really doing this once, usually you make a mesh, you find these conditions, you do that once, and then, you know, you never have to touch it again. So you really want to be hands-on with computational savings and take kind of a practical approach. The same is true with this numerical dispersion. You can exactly figure out whether your seismograms are resolved or not by, I mean, actually running your simulation on 2 different meshes and comparing the synthetics. So there's very practical ways to get exactly the answers that you want, which obviously the computer simulation not crashing is a starting point, and often that involves changing the time step. Yeah, questions though, raise your hand or unmute if you have questions. Akash, I think with all these questions about time
Yes.
steps and stability conditions, we should introduce your other example. I know I was suggesting cutting one, but
yeah, but I discussed the final example.
Okay, so you want to just go through the doubled element size?
Yeah, that was the third example. So the first one was okay, I'll just recap. So first we did this homogeneous half space model. Then we added a layer without changing the meshing. So that was this model, which has this plotting artifact. It's 2 layers, but it seems to be 3 layers. And then in the third example, we just doubled the element sizes in the bottom higher velocity layer. So that's what you want to do ideally. And if you have like a 7-layered model, you can build upon this concept and like have your 7 layers. So you will have, instead of these 2 regions, you will have 7 regions, and you will have 7 interfaces, 7 interface file, and then 1 interfaces file, which will have details about those 7 interfaces file. And then you will have these 7 model definitions as well. Yeah.
I thought possibly there was going to be a complete doubling of all element sizes or having.
I don't have that example, but yeah, like if you want to talk about that.
Maybe it's just a point to mention that the idea that if you want to go from 1 Hertz accurate simulations to 2 Hertz, the basic rule is that you're going to have to cut your element size in half, which results in 8 times as many points. And you're going to have to cut the time step also in half. So it's a factor of 16. And this is kind of a good rule of thumb to explain why it's so important to know scientifically what target frequency you actually want. And it's also a huge advantage because you can say, instead of thinking, wow, it's going to be 16 times more to go from 1 hertz to 2 hertz, you could be turning that around and saying, you know, to go from 1 hertz to a half hertz, it's 16 times cheaper. So it's really important before you go off the deep end to know what your target is. And sorry, there was a hand up there. If you could ask that question. I can't imagine I was answering it, but ask. Yeah, go ahead.
Yeah. Thank you. It was just for external tomography models. I don't know if you talked about it already, but are there tools to know where to put the interfaces and to make them?
So you're saying that in the external tomography file, so I just want to distinguish between two things. If you grab a file from Iris that has volumetric field that has an interface, SPECFEM isn't going to magically kind of like bring in a mesh elemental boundary there, but it will bring in the volumetric field. So is your question about meshing or is it about the model? Like,
it's when you don't want to use a pre-made Earth model and you use one that you put in a tomography file, and you can put it like this. And if you want to add interfaces, you need to make your interfaces files.
Yes.
And how do you put them? Depending on the tomography
I can take
file.
that.
Go ahead.
Carl, do you want to? Okay. Yeah, so basically when you use a tomography model, the tomography model will be like, if you look at the tomography file, it will have these XYZ coordinates, and then you will have model values corresponding to those XYZ values. So that's just the model definition. But your mesh, you will have to define using your mesh par file, unless you are using an external measure. So here we have been discussing the internal measure. And for that, if you have some sense of your tomography model where the velocities increase, there might be some anomalies, but like the big picture view, okay, this layer is slow velocity, this layer is high velocity. You can design your interfaces and your element sizes just based on your idea of the model. And that definition will come through the mesh par file that we just discussed. The N regions, N materials won't be important here because it will get overridden by the tomographic model file. So when you do the generate databases, and if you have that tomography model flag on in the par file, it will read the tomo files, but it won't read the material definition within the mesh par file. But it will read the region definition and the interface definition from the mesh par file. I realize I said a lot, but I hope that was like you got something.
Thanks.
Go ahead, Luis.
Hi. Yes, I guess I don't quite understood Akash. I didn't quite understand him. Sorry. So for example, let's say that I wanted to simulate an earthquake in Southern California, and I take the as community velocity model from SCEC. I have those like text files with X, Y, Z, and the model parameter values as well. So I input that model into SPECFEM, but I still need to construct the mesh myself.
Yes. So
yes.
The mesh you have to construct, and once you have your mesh defined, then your model parameters will get interpolated onto those mesh element nodes if they don't exactly fall, like overlap. So
I just wanted to add to that. Yeah. The only practical information you need is the topographic surface and the bathymetric surface. At a higher level, if for some reason you said, yes, I also want the mesh to conform to the moho or the basement structure. I mean, you could do that, but for all intents and purposes, to make the mesh for Southern California, you need the topography and then some decision about how many doubling layers to use, for example.
Okay, but I'm sorry. So the way I say it is that, for example, I can define layer in my mesh that will correspond to the crust, but that layer will have different parameter values, right? Different VS and VPs. So my question is, as I understand, I have to define a specific value for each part of my mesh, right? Or each part of the layer. But if that layer has different values, do I have to subdivide that first layer into different sections in the meshing? Or I don't know if I explained
It's not
myself.
necessary. It depends on how specific you want to be. I guess there is a way to like define every element manually or something like that using external meshes or things like that. Internal measure is kind of a simplified form. If you are okay with a general layered model, you can have some average element size for the top layer, average element size for the second layer. There might be, the velocities might change within that layer. So the mesh layers are different, can be different from the model layers. And then looking at the model, which might be very, I don't know, heterogeneous or like not that regular, you can still use a regular mesh for that not so regular model and run simulations. But if you want to be very precise, you can use some of the other tools to have very specific meshes for your specific cases. You have a high velocity anomaly in your model and you want very large size elements there, then I think there are ways to do that, but yeah.
So sorry, say that I have the minimum velocity in the crust. To resolve the frequencies I want, I will have to specify the size of the element, and that layer that will correspond to the crust will have the same size for all the elements. And then the model is going to be interpolated in those grid points. Is that correct?
Yes. Yes.
Okay, thank you.
Yes, yeah. You can customize your mesh. I think there are ways to do that, but that's the general idea. It doesn't need to be the, like every change in velocity has to have a different element size. It's not necessary. It depends on how precise you want to be.
Can I interject just for a second? You know, what we're getting at is that there's a sort of like desire for the mesh to look very much like the structure you're modeling. And there's a great paper by Marco Stupenzini in 2009 in the Grenoble Valley, I think, where they have a basin that's exactly complicated mesh. There's even a bridge in one of these simulations. And so the desire to exactly have that connection makes sense. But I think from a practical standpoint, it's also a huge amount of effort. And the real question is, do you have to have these elemental boundaries exactly matching your model and the structure? So in all the work in Southern California, we don't have, for example, elemental boundaries matching the basement of the Los Angeles Basin or San Bernardino Basin. It's very accurate to have just a lot of GLL fine points as you're getting at the size of the element being super important. But your mesh doesn't have to look like the structural model, aside from the topography. That's why I said you really need the topographic surface to make any mesh. Go ahead, Ashton. I know he has a lot of experience. Go ahead.
Sorry, not to beat a dead horse, but I guess I have a similar question. And so, yeah, ignoring the requirement for topography or bathymetry and ignoring, yeah, I'm not going to try and match mesh layers with known geological structure. But I guess my question is, if I wanted to take an a priori velocity model, like something from CVM, and I wanted to do a forward waveform simulation in that model, reproducing the best that model can. So reproducing, you know, minimum geological structure imaged and wavelength and things like that and frequency. How would you, Carl or Akash, go in creating that mesh? Like what would your actually specific steps be, if that makes sense? Would you define a qubit model that best represents that? Or would you just take that velocity model and, you know, write Python code to interpolate it yourself into a new mesh? Or what would be your process?
like I can give some basic insight and then probably Carl can take on from there. So basically, I am still sharing my screen, hopefully. So here, like the mesh criteria, basic theory, you can like an idea about these theoretical constraints, I think come from these two conditions, how many grid points you want per wavelength, and then the stability condition. But yeah, exactly how to implement it in SPECFEM, what would be the better approach, internal mesh or the external mesher? I think for that, I'll pass it on to Carl probably or someone.
I mean, I would say, I like this general question. You would start by just saying, I have a homogeneous mesh. You had said no topography, just the simplest imaginable mesh. Get the elements the right size, get the accuracy you want. And then your questions shift to, how can I be more computationally efficient? The only reason we use doubling is for efficiency. The only reason we try to get a long time step is for efficiency. We could use a much shorter time step and just waste all that cost. We can use, you know, very, very small elements and waste all that computational cost, but we're looking for the fattest elements and the longest time steps that give us the seismogram accuracy we want. And so that's the way I would say. And then if you say, I've got this crazy, super slow, compact anomaly here in this large domain, well, maybe you need to, you know, at that point, go to more sophisticated ways to mesh that smaller body with smaller elements. But the starting point is just use the simplest imaginable mesh with small elements and then start making them larger and then start. Andrea, go ahead.
Yeah, no, I also wanted to say in that part that apart from that, doing the doubling just to have like optimization in the mesh in the 3D Cartesian, I will take care of the size of the step size which you have in the material model. So when you are having the interpolation between those phases, you don't have like a big jump in the material properties, because the idea is that you are changing a layer in those limits of the mesh. So that's also a point to take care of when you define the material properties model that is different from the mesh. And for the mesh, for instance, for the question that we had before is that if you are in the crustal layer of the regional model, like in just very close to the surface, I will go for an element size that will represent the minimum velocity of that layer and the maximum frequency you want to propagate. And then you just increase from there, depending on initially starting what are the variations on depth of your model. That's what I would do in that case.
That's a great point. Take the worst imaginable layer, which is usually the shallowest one. Like if we say, oh, I want VS 800 meters per second for some sedimentary basin, that choice is that's going to be your problem, you know, to target. And then you say, well, I don't want to give the whole upper mantle something that would resolve 800 meters per second, but it'll work. It'll give the synthetics you want.
Also, yeah, it's a compromise, right? Because I remember when I was running simulations for Bogota, the basin in Bogota is very like soft materials. So you have to compromise. Okay, if I want to like propagate 5 hertz, 10 hertz, then I have to check if I am able to represent the minimum velocity of the basin, because it might be way too small. And so you have to have very slow elements. So you have to compromise, or minimum shear wave velocity you want to propagate, or maximum frequency is like a compromise in the mesh that you have to make, depending on the computational resources.
Go ahead, Robbie, and then Ashton.
Yeah, so correct me if I'm wrong. So the doubling is mainly used if you have, for example, if you want to add 2 different starting velocity model, or if you want to increase the mesh size so that each of the different part of the model vary differently. Is that correct?
I think the answer is it's only for computational savings. There's no reason, if you have two bodies, 2 different materials, there's no reason you have to have doubling. It's just something that is kind of a sensible thing to do to make the most of the resources you have. I mean, I think you could take this to sort of like green energy argument, right? We're using energy to run these computers and air conditioning. So at some level, it's like, let's be efficient. Yeah.
Yeah, but if you change the mesh size, similar to what we're seeing here, do we have to put the doubling, or we can just do it without the doubling?
If you do it, yeah, go ahead.
Sorry. Yeah, like if you look at the second example, we ran the exact same model.
Yeah.
We have the exact same seismograms out of example 2 and example 3. The difference is just that so I was not able to run the third example, but I'll show you this completed notebook. So the second example ran in 3 minutes, 36 seconds when I ran it. And the final example ran in 1 minute, 22 seconds on this container setup. So I saved like, I don't know, 60, 70% of the time, right? So that was the purpose. But if you look at the seismograms here, and if you look at the seismograms here, like visually, they look exactly the same. So you don't have to, if you have that much time and computational resources.
Yeah, I get that. But so if you look at those two mesh, you can see that there's a difference in mesh size. So below, the mesh size is much coarser compared to above. So basically in the red. So the question I asked, if you have a different mesh size, the way that it's showing here, do we have to always use the doubling when you change the mesh size?
Yeah, so like if you don't have a gradual transition from small sized elements to larger sized elements, like if you imagine this element right here.
Yeah.
So this node has to interact with the bottom node from the bottom. Otherwise, like there will be some kind of discrepancy when you do that finite element based integration. So, like if you have in this volume, like this cube, it's not exactly cube, but let's consider. So in this element, you have 8 nodes, but here you will have, I don't know, like many more nodes. So there should be node to node interaction for your finite element scheme to work. So if you don't have this transition, you will be just like this node here won't have anything to interact with in the bottom layer. So your finite element scheme will break down. So that's why you need this transition using a doubling layer, or there might be other strategies as well, but this is what is inbuilt in SPECFEM. So here you will see in this doubling layer, every node has something to interact with. It's not like it's in the middle of a element boundary or something, element side.
And this is where, I mean, we're getting toward the meshing side, but this term unstructured meshes, which sounds like a negative thing, is a positive thing in the sense that you have different number of elements meeting at these points within the mesh. And so this unstructured enables a lot of these properties that we see. I'm not sure we answered that really. And I'm not.
Yeah, I get it. No.
Okay.
Yeah.
But I really like Akash emphasizing this, 1 minute, 1 minute, 30 seconds versus 3 minutes, it doesn't sound like a lot to us waiting here, but then you think, oh, I'm going to scale this to 1,000 times. And then you're realizing you're talking about 1.5 weeks versus 3.5 weeks or something like that of runtime.
Can I say also something else?
Yeah, go for it.
Like when you are doing the doubling, you have also to take care that in the part of the model that you're making the doubling, the material velocities will allow for the propagation with the maximum frequency. So in that part of the model, what you are doing the doubling, the size of the element should be related to the maximum frequency and the material in that zone of the mesh. So that's something you take care when you decide where to do the doubling. You see at the VS and you see that doubling the element on that area of the domain will be enough for propagate with the maximum frequency you want to propagate in the whole domain.
Yeah, great point. I mean, basically what you hear is that the mesh doesn't know anything about the model, but you can't make the model without knowing the mesh. You really, at this level, you have to be thinking about the two together.
Yeah, Carl, may I add something to what Andrea said?
Sure, yeah, go.
And indeed, that's a great point, because you really need to concern about the resolution that they achieve from these simulations. What's the highest frequency that you are aiming for resolving? And in that case, this is what is known as Cron condition, where you need to take care of the ratio of the spatial and the time sampling, how you are discretizing your model, like in both in space and time, which cannot be done randomly. Otherwise, you may easily have lots of numerical instabilities. If you are lucky, your code may blow up, your numerical simulations may blow up. If not, then you may have some numerical noise, numerical anisotropy, etc., that you are not aware of. And you may try to model some numerical artifacts like that. So meshing part is super critical, in short, that may need a separate workshop maybe to go more, dive more into details.
I did say we weren't going to be talking about meshing, but we should talk about it because it's certainly, I mean, practically we used to always use the external mesher, but I found us all in my group drifting back toward the internal mesher because it does the things we need. It's open source. It's right there in the code with few parameters, but this will depend on how complex your needs are. I feel like we've tapered off here. Let's use this time. First of all, big thanks to Akash for pulling this all into the notebook, especially. I agree that seeing it here instead of the README is really nice. I'm going to propose we take a break until 40 minutes past the hour. So that's basically a 15-minute break right now. This is our main break. And then we will finish, we will shift into Bryant doing the adjoint capabilities and see where we go. But I really appreciate everyone's attention here. During the break, people might be around for questions too, but probably the hosts here will take a break too. You're welcome to ask questions and see if there's any answers. All right, thanks everyone. We'll see you in 15. Are any hosts out there available to help someone in a breakout room?
Yeah.
All right. Thanks, Amanda. Someone just asked for help. Hopefully people are coming back in the next minute or so. Let's see. Akash, I was
Yes.
wondering if you'd be willing to give like the 5-minute just showcase of some figures that you made in the 3D kernel example to motivate what Brian's going to be doing. We don't have time to do it in detail, but I think it would be ideal just to bridge the gap, between, we've got the 3D code set up, we saw Chinya's motivation, and then
we can do that.
Okay. I know this is just the reality. I'd much rather hear people interact and ask questions along these topics than us just show more than we'll wait. Let's wait one more minute here. We could take a poll to say, are we ready to go on? But it's hard to know. We'll go on one way or another. Yeah, a lot of discussions about 3D models. This obviously isn't a focus of the workshop, but it's the people who've looked into SPECFEM, that's what they want to know. Like, how do I take this model, get some synthetics that are numerically accurate? And that's something that we should be looking toward. Gmesh, yep. Those are all lots of pros and cons of these meshing things. I feel like we've watched them for decades now. Well, Akash, why don't you kick things off? Hopefully everyone can come back here.
You want to do a poll?
Sure. Well, it's more like, are you there and ready to move on? But we'll get a lot of abstaining, so are you guys ready to go? So there's 113 people, which is excellent. And I think we're going to now, just to set up this next item, is to say that, Chinya gave this talk on the kernels. And one of the things that I really hope to see is that when you go into a code, it's nice to be able to say, I've seen this paper. I'd like to be able to verify those results before I do my own thing. And so Akash is going to show this example that he actually added into the software suite this summer, that reproduces the kind of seminal kernels that Chinya published in the 3D paper that basically documented, hey, SPECFEM has adjoint capabilities for making kernels, which she did back in, 2005 or something. Okay, so yeah, Akash, we've got everyone who's responding, which is 73 people saying ready to go on. Let's go for it.
Okay. Do you see my notebook?
Yes.
Okay. Yeah, so I think I have like 5 minutes, so I'll run through this. So basically, there's a notebook I prepared last night, so you won't be able to find it in the adjocs folder. And I was initially thinking of making a slideshow, but this seemed a better way to represent some of the things I want to show. So basically,
zoom in a little bit, Akash.
Yeah, sorry.
Could you zoom in a bit on your screen?
Oh.
Just so people can read it.
Is it better now? Or do you want me to zoom a bit? Is it okay or more?
That looks good.
Okay. Yeah, so basically, I'll first tell you where to find the example. So if you go to the SPECFEM 3D directory, I already told you, in the examples folder, you have the sensitivity kernels, LewTromp 2006. So if you go to that file, you will have a README file, which will guide you through the steps needed to regenerate those results and all those kernels, banana donut kernels and the other kernels. And then you have this data folder, which has the source. So here we don't have a CMT solution, but we have a force solution file for the source, meshframe 3D files, which defines your mesh and the model, par file for your simulation parameters, and the stations file and stations adjoint file for your adjoint simulations. So the instructions are very clear in the README file. And then you have a source time function, because here we are using a specific source time function. So that's why we had to supply this externally instead of using the default source time function. And then there are some reference folders for reference seismograms, adjoint sources, and kernels that you can check whether your simulation ran correctly, and you can tally those. So it's there in this folder, examples, sensitivity kernels, Neutron 2006. So I'll just go through that, but you can read the README file and figure it out. So mostly these are the steps just taken from the README file. There is this user T0 parameter, which you want to set sometimes when, especially when you have multiple events. So this actually starts your seismograms from, so if it's 10, your seismogram would start from -10. So it gives a buffer to your seismograms for different events with different half durations, so that your seismograms basically start from the same timestamp, the -10 seconds. And that kind of reduces a bit of the confusion. But it's probably not necessary for a one source receiver case, which I'm going to talk about. And then, in addition to those MeshFrame 3D, XGenerate databases, and SPECFEM 3D, you need a few more utilities like this XCombine volume database. So if you're using multiple cores, you need to combine the slices to view them together. And then this travel time, I don't know where that is. Probably it's in the next step somewhere, but you have to compile that. Utility to actually compute the X-create adjoint source travel time. Yeah, here it is. So you have to compile this utility also. I think it's already compiled in the container, but yeah, you would need these two to calculate your adjoint cross-correlation travel time sources. So the forward simulation, this is a slightly different homogeneous half-space model, but very similar in concept. There's a VPVS value. Your source and receiver is separated by 100 kilometers at some depth, which I cannot recall. And then you have this ray paths, direct P, direct S, SS, and then you have SP and PS. So for all these kernels, like a P kernel, S kernel, you'll have to take specific windows corresponding to those phases, and then run your, take them as adjoint sources, and then run your adjoint simulation. So yeah. So this is your force solution file. I'll just skip through that. So for your P plus SV simulation, you need a force in the X direction, this direction. And for your SH simulation, you need a force in the Y direction. So you get the SH waves. So you have two different force solution files depending on which simulation you are doing. So basically there are two simulations depending on the kernels you want. Source time function looks like this. 1 point to note in SPECFEM, like generally source time function refers to a moment rate function, but in SPECFEM it wants the cumulative moment released function as the source time function. So there is some, there can be some confusion regarding that, but it's spelled out in the manual. So that's one thing to be careful about. So here we are using force and not moments, but it's the same concept. So for the PSV simulation, if you do like with a force in the X direction, this is what you get along the X, Y, and Z components. So basically you are exciting the X component and you get the P wave and the PS SP wave and then the SS wave. So from the PSV simulation, you will take windows of the P arrival and the PS plus SP arrival for the corresponding kernels. And from the SH simulation, you will take the S arrival and the SS arrival from the Y component for your S and SS kernel generation. So to make the kernels, you have this X-create adjoint source travel time executable, and you specify the window, and then there are which component you want. I guess this is X, this is Y component, and then you specify where your seismograms are. So this cross-correlation travel time adjoint sources will be derivative of your displacement function that we saw.
Can we pause for a sec, Akash? Someone was asking about this particular notebook is not available. Is that right?
Yeah, so I told, like, I made this last night instead of, like, I transferred things.
Okay, so that was answering a question. Someone was expecting to see it, but maybe since Brian's going to go, I mean, you've laid out the details in the README. That's one of the points to make, that all this is there.
Yes.
How about we just get to, let's just show some of them.
Okay.
And possibly, do you have any images from the Lou Trump paper or that we could also show?
I don't have, but I can like share screen and probably show.
Yeah, maybe. Sure.
Yeah. So let's talk about this for a moment. So there are some visualization instructions in ParaView after you run that joint simulation. And yeah, you set your, basically this color scale is very important. As Chinya said, if you don't set it properly, you won't see this. And so yeah, this is a P wave sensitivity to the p-wave velocity model. So you have all these kernels. P beta kernel means sensitivity of p wave to the shear wave velocity model, which is like order of magnitude less than this, because you are looking at the p wave sensitivity to S model, and we have some figures like that. S wave sensitivity to the shear wave velocity model. So these are more or less the figures you will see there. And then you have similar figures for the SS arrival. So this is the surface. There's a different kind of cross-sectional view compared to this one. And then I think I should pull up this.
Can you pause? Just slow down for a second here. So yeah, Akash is showing the source for this toy problem is buried at some kilometers depth. So you're underneath looking up toward the surface at the reflection point of the SS wave. Okay.
So there is also the second leg from the surface to the receiver, which is on the other side.
Definitely. We're seeing half of the kernel.
Yeah.
Yeah, we are seeing half of the kernel. The other half is on the other side, which is kind of, blocked. So I'll pull up this paper. I'll stop sharing. I'll share the paper. Let me see.
I also want to emphasize that those kernels will not run in your notebook because these are kind of research grade in terms of the memory requirements for running those. So what the notebook can show is sort of like a very nice display of what the example output figures and files look like. But don't get the idea that I think you're going to run those kernels on your laptop unless you have a really impressive laptop.
Yeah, can you see the paper?
Nice, yeah.
Yeah, so these are the kernels, and that's what, those figures are pretty much similar to these. The sections might be slightly different, and the perspective, but more essentially the data and the information is same and the color bars. So if you want to regenerate these kernels from this seminal paper on this topic, you can use that README file and see through the steps. So yeah, the critical things were like the source time function and those kind of things you have to be careful when you set up your simulation. So yeah, I can end there if you say, Carl.
Let's go back to you. Yeah, well, I think that might be enough to get a sense of what these much more complex examples are in terms of requirements, but still we're talking about a homogeneous model. So in some sense, it's not complicated at all, but the sort of reproducing the published results has some features that will, technical notes like the implementation of the source as a force or the external source time function. In general, you don't need any of that for making kernels, but if you want to understand exactly what was done in this study, that example is in the SPECFEM package. I'm really happy that hosting this workshop kind of motivated me and really asking Akash to try to bring this into the package, because I think if you're looking into SPECFEM, it'd be nice to say, yeah, I can do that. I can do that example before moving on. There was a question up. I'm sorry, I missed it. There's a hand up. Is there any question right now about this? And I think Bryant also said we can add this notebook just to basically conveniently browse what Akash has done, but not run these simulations. Akash, could you comment on how many cores you ran that on?
Oh, so this was not run on the container.
I know,
but not set up to but yeah, I ran it on 40 cores, I guess.
Okay.
I, in fact, probably ran it on many more cores, but for the example part, it has 40 cores so that everyone can run it on whatever cluster they have.
Okay.
The PAR file is set up with 40 cores. Yeah.
You just have to wait longer than, so some of the trade-offs aren't memory limiting. They're just how long do you feel like waiting? If you have access to hundreds of cores, you wait less time, but it's probably what you're saying is that it probably can run on fewer than 40, but there's some limit where it probably won't run at all. Go ahead, Carrie.
Hi, thanks. So I have a question which will be very strange for people working on Earth, but do you have to know what your phases are? So you're estimating your kernel based on, I think this is an SS.
No, you don't have to know anything.
Oh, great. That's good. I don't know anything, so that's good.
Yeah, indeed. This is the beauty of these methods. You can just compute the sensitivities to any wiggle that you don't need to worry about. And actually, this is the motivation for waveform inversion, because when you're using ray-based methods, you really need to isolate these phases, right?
Yeah.
Because it depends on the success of your inversion, depends on your ability to isolate and remodel these phases. In case of full waveform inversion, actually, if you are not directly interested in a specific phase, you don't need to worry about any contamination by other phases. So you just select a window, time window of interest, and then go.
Okay, great, thank you.
I'll just mention one final point. Like when I share this notebook, probably at the end of today or tomorrow, all these figures that you see in the notebook are just taken from the reference folder within the example folder. You are not running the simulation here, and I don't think we can run it in the container probably. So yeah, it will just be a notebook which will populate the figures, but nothing more than that.
It's still nicer than, going into the terminal and LS and more and so forth. So that's really nice. Yeah.
True.
All right, let's move on. So that was just to sort of the continuity. I feel like we had the Chinya's opening talk, Akash introduction to the 3D code, the seminal kind of 3D kernel examples. And now we're going to go step back toward thinking about how these, things related to the adjoint source. And for this, we really don't need to be dealing with 3D codes or anything. So Bryant, go ahead.
Yeah, hi everybody, I'm back. And I'm going to lead you through the day 2A notebook, where we're going to talk about how to generate some of these kernels on your own laptop using the SPECFEM 2D package. So hopefully you're at this page, and we're just going to go to AdJdocs, workshops, and we're going to click on this day 2A kernels notebook. When I was reading through some of the survey responses from yesterday, and some people had asked for a little bit more motivation at the start of the notebook. So I've added just like a small figure here so we can kind of understand what we're going to be doing throughout this notebook. Some others have asked for, a little bit more discussion time. So hopefully we've been accommodating that for you. And others were asking for a little bit more hands-on stuff. Definitely kind of running through cells in a notebook is a bit more abstract than actually being able to run some code yourself. So there's a 2B kernel exercise notebook that hopefully we can get to today. But if not, then maybe we can save that for tomorrow. So here we are at 2A. We're looking at kernels and adjoint simulations today. Both Chinya and Akash gave us a really nice introduction to kind of first of all, the theoretical background of what are kernels and how are they generated mathematically. Akash showed us some figures of these kernels generated in 3D, and so now we're going to actually manually step through this process in 2D. And we're going to try to do it from the very beginning. So here's this motivation figure. This is from Carl's 2007 paper, has been shown a couple of times already, where we're just looking at, if I zoom out, looking at the propagation of the forward wave field. This is time, the lowest time, shortest time at the bottom going upwards. So you can see the stars, the event, the receivers, the triangle. You can see the forward wave field going outwards. Something that Chinya talked about is when we want to do the adjoint wave field, we need to inject something like the data residuals at the receiver location. So you can see that going backwards in time, the adjoint source propagating outwards, creating the adjoint wave field. And then in the adjoint simulation, we're creating this interaction field and actually integrating over space to create this cigar-shaped sensitivity kernel. So that's exactly what we're going to do today. Starting from the beginning, we're going to do some forward simulations. Then we're going to learn how to set up the adjoint simulations, and then we're going to run an adjoint simulation and look at the kernel output. And hopefully by the end, you'll be an expert in adjoint simulations. So just going into section 1 here, we're starting with setting up this SPECFEM 2D working directory and importing our Python packages again, very similar to what we've been doing in the last couple of days. So here we're just, all these packages are going to be used for calculating misfit, for plotting some waveforms, and for plotting the model. So I'm running that first cell, and then I'm going to run the second cell right after, which is what we did in day 1 and what we did in Akash's notebook, is creating this separate SPECFEM working directory, which is going to sit on your local machine in your local file system. And it's going to have those important directories, the bin, data and output directories. Yes, I'm going to zoom in, sorry. Hopefully it's more readable now. So yeah, just ran that cell. And now I'm looking at the bin data and output files directory. And so now we've got a kind of clean working directory, and we can go into looking at our experimental setup. So I'll kind of power through this, but when I get to the next section 3, I'll take a stop so that people can catch up and make sure that we're all on the same page there. So this section 2 is just trying to visualize our experimental setup, just to give us some context of how we're gonna approach the adjoint simulation. And it just kind of explains that we've got 2 models already available in our data directory. The first one being a homogeneous half-space model, which is kind of what we saw towards the very end of our day 1 notebook. And then we have a new model that we're going to look at, which is a perturbation checkerboard. And this idea of a checkerboard will make a little bit more sense when we try to visualize this. And the idea here is that we are using this checkerboard model in order to generate our data. So kind of throughout today, you've been hearing that in our adjoint simulations, we're propagating in residuals, so data synthetic misfit. In a kind of ideal real world inversion scenario, your data would be like actual seismic observations, things that are coming from your seismometers that are recording earthquakes. But data is messy, data can be difficult to work with. And so to kind of simplify everything in this notebook, we're actually just going to generate our data synthetically. And that way we already know the kind of model that we're trying to approximate, and kind of know that everything's being well behaved because we're generating everything synthetically.
I'll just pause, Brian, to say that this is the widespread approach in, say, industry, where you're going to test some particular aspect of a convergence or optimization algorithm. It's often the case where you have a target model, target synthetic. So that aspect we're normal.
Yeah, definitely. And that's a really good point that I wanted to kind of add to, is that a lot of published inversion studies will start off with a checkerboard inversion, with a completely synthetic inversion. And this is really just to illustrate, like my experimental setup is valid. We have the proper resolution that we can actually, and that our methodology is working, that we can actually recover a model that we know. So I'm going to run this cell. It's just putting me in the correct directory. And then in section 2A, we're going to look at this homogeneous half-space model again. This is the same kind of code block that we saw in day 1. It's really, it was when we were looking at the PAR file, we kind of saw how the mesh and the model were defined, and we took those values in order to generate, in order to kind of just plot on the fly a homogeneous half-space model. And the idea here is that we've done this already, but it was kind of for contextual visualization so that that this is our starting model. It's just a square in the X and Z components. We're actually looking at, if you look at this motivation figure, which is what we're going after, this is actually Southern California. So we're actually kind of rotating our 2D domain so that we're looking at the kind of XY plane. So this would be the surface that we're plotting waves on top of, or that we're simulating waves over. So that's our homogeneous half space. And if I go down to section 2B, now I want to look at this perturbation checkerboard model. This is also available in the data directory. And this kind of touches on the external tomography models and files that we were discussing during Akash's notebook. In SPECFEM 2D, this is kind of a particular format of a file, but it kind of shows you how you might approach using external tomography files. It shows you kind of the format that that you might expect and how SPECFEM might try to look for these files. So here inside of our data directory, we already have this model velocity.dat checker. And if I print out the top lines of that file, you can just see that it defines coordinates. So these are X and Z coordinates, and then elastic parameters. That's density here, VP and VS in meters per second. So if you go into like SPECFEM 3D and you define external tomography files, they're very similar. They're like these XYZ files that define coordinates and define material parameters. And we can plot that just to make it a little bit more accessible. And so this little Python code block is really just reading in columns from this text file and using Python to plot it. And here we're going to try to plot VP in meters per second. Running that code block, when it executes, she'll put a nice little checkerboard model.
All right, let's do a poll. Do you
Did you
see a
make the
nice
checkerboard?
little? Do you see a nice little checkerboard model on your own notebook? Is the question. Okay, good enough. And if you need to go to a breakout, just say breakout. See you there. Go ahead.
Cool. So this is our target model. So this is kind of the known model that we're going to use to generate our data. If I run this next code block, well, we're just going to plot VS, which actually looks exactly the same. You can see from the color bars that they have different values. And one thing that I want to note is that if you look at the mean value, so essentially like the homogeneous model on which these perturbations lie on top of, the white color here is about 3.5 kilometers per second. And if I look up at my homogeneous half space, you can see that it is 3.5 kilometers per second. So the idea here being that we are applying these kind of perturbations on top of the homogeneous model. So we have these regions of slow and fast velocity. And the color scheme is red colors are relatively slow velocities, blue colors are relatively fast velocities. And that's kind of the standard color scheme that we would have in seismology probably and in seismic imaging. And then just to further contextualize the problem, we've got sources and stations. We've kind of been harping on these files. Stations are defining where you want to retrieve your synthetic seismograms. Sources define the event locations and how the sources are initiated inside of a simulation. So in that data directory, like we looked at yesterday, we've got this stations file, and we've got 25 source files. So this little code block is just reading in all of the stations inside that stations file, reading in all of the sources, and grabbing coordinate information just so we can plot it on top of the checkerboard so that everybody kind of understands the experimental setup that we have here. So here in this figure, you're seeing the checkerboard again. All of the yellow stars are the events that are available to us, and all of the upside down blue triangles are receivers that are available to us. When we continue on this notebook, we're only going to take one event and one receiver, but when we get into the exercises and as well the imaging notebooks tomorrow, we'll be able to access more of these sources and stations and use them kind of in order to do our imaging problems. And the next couple code blocks are just to plot the text, the names of the sources and the names of the stations, just so, you know, if you're running through the exercises or if you're a bit confused about, you know, which source file corresponds to which star, it's a little bit easier for you to figure that out. And this one's going to be super messy because the stations are all one on top of each other, and I couldn't find a good way to plot the values, but hopefully you can read some of the values in there. And finally, this last code block before I take a little break, it's just plotting the experimental setup that we're going to use for the rest of this notebook. So we will really just want to use a single source and a single station in order to keep things simple so that we can kind of visualize one of those cigar-shaped sensitivity kernels or misfit kernels. And the idea here is we're just grabbing the first station and the first event out of that list that we created and plotting them on a line. So you can see that, you know, the ray path, which connects the source and receiver, is going to go through this relatively slow region and then through a bit of a fast region. So that'll influence what our output kernel looks like. And so yeah, maybe I will pause there for a couple seconds and let people catch up. If anybody has any questions on the experimental setup, happy to answer them. Or if we're all good to go, then we can power through.
I'd say go forward based on the poll. Yeah.
Cool. So here we are. This whole section 3 is really the meat and bones of everything we're about to do is how do I actually get to a point where I want to run an adjoint simulation? And so in order to really get here, we're gonna have to run a couple earlier simulations to create our synthetic seismograms for the synthetics and data. Just some useful definitions here, kind of harping on what Jinya and Akash have been saying. The adjoint simulation is the interaction between the forward and the adjoint wave fields. That forward wave field is our source propagating from event to receiver. I forgot what the other words are. The adjoint wave field is our data residuals being injected at receivers and interacting with the forward wave field. And the kernel is the kind of integration that we get out of it, which is what we're really after, this kind of cigar-shaped sensitivity kernel. So the first thing that we have to do is run forward simulations. We need to generate our data. We need to generate our synthetics. So this first code block, really similar to what we did yesterday in day 1A. I'm essentially just setting up and running a forward simulation. I'm going to run this and then kind of talk about each of the individual lines of code as it runs. So idea being that if you remember, SPECFEM is going to look for a source file, a stations file, and a par file. In the example problem, these are not available. We have suffixed versions. We've got source 1 through 25. We've got this checkered stations file, and we've got a couple of par files. And so really these three code blocks are just making sure that we're using source 1, we're grabbing the first line of the stations file, and we're copying in the correct parameter file, which is set up to run the checkerboard model. These parameters we saw yesterday, but I'll kind of explain again. The end step is the number of time steps. This controls how long your synthetic seismogram is going to be. And this is kind of an arbitrary value, but we wanted to match between the target synthetics and the data, between the data and the synthetics. And so the values are different in the two par files, so we're just changing that here. And then these things we saw yesterday, we're essentially telling SPECFEM that we want to output our database files and our model files in this Fortran binary format, so that we can use it, so we can use them for visualization. This is the checkerboard model. So this is that kind of external tomography model. SPECFEM just kind of expects it in a specific file name scheme. And if you were to try to, if you didn't run this command and you tried to run the simulation, it would crash and just complain that it's looking for this file. And so that would kind of indicate to you that you need to rename your starting model. And then we're running MESHFEM and SPECFEM with one processor here, and just moving the output files to a safe space, because when we run our next simulation, if we didn't move our files, we would be overwriting the synthetics we just made. And so this is kind of a typical thing where if you're doing a lot of bookkeeping when you're running SPECFEM manually to make sure that files are in the right place, that they're named the right thing, and that you're not overwriting if you're running multiple simulations one after another. So cool, that's just printing out the end of that parameter file. I talked about kind of what the changes were that we made to the parameter file. And just one note that if you did try to change this MPI run to a higher value, you would see a really funky velocity model because of the way that we're defining our external tomography model. So just in case anybody took it into their own hands to run with more cores, you might see some weird results. And then we can look at the seismogram. We only really expect one seismogram out because we have one source and one station. So if I run that code block, I'm just plotting that single seismogram using a SeisFlows utility function, which is obfusc under the hood. I'm saving it to a PNG file, and out should pop a synthetic seismogram that's pretty simple, representing wave propagation through that checkerboard model. So maybe we can pause there and make sure that everybody can see this synthetic seismogram.
Here comes a poll. Did you generate the same seismogram or see it?
Yeah, try to keep all these kind of bookkeeping things in mind, because in the exercise, we'll ask you to change some parameter file, par file parameters, in order to kind of set up your forward simulations and your adjoint simulations. So just keep a note that like where this was happening in the notebook, so that if you need to come back and reference that, you don't get lost. Okay, section 3B. Now we're doing the exact same thing, but with our initial model. So what we just did was we ran a forward simulation through our checkerboard model. We created our data or our target synthetics. Now we need to actually create our synthetic seismograms. So we're really doing a very similar thing. Our source and station file is already set up. We're setting up a different parameter file, which internally defines our homogeneous half space model, but on the same mesh. These parameters, I just run this so I can wait for it. These parameters are very much the same, except we want to tell SPECFEM to use our stations file rather than using its internal definition of the stations. And this save forward is actually a very important parameter. This is what Gina talked about in her presentation, is that when we run our adjoint simulation, the way SPECFEM does it is that it takes the last frame of the forward simulation and runs it backwards in time against the adjoint simulation in order to produce the kernels. So we really have to tell SPECFEM, hey, at the end of this forward simulation, I need you to save the last frame of the wave field so that we can have it available to us in the adjoint simulation. So if you were, for example, to not set that flag and then you ran your forward simulation, when you went for your adjoint simulation, SPECFEM would complain and say, hey, you didn't tell me to do this thing, so I can't do that other thing. And then we did kind of the same thing, ran SPECFEM, ran MESHFEM, and moved our files to a different directory so that if we were to run another simulation, we wouldn't overwrite existing files. And you might see that I cannot remove. This is in case somebody already ran this text block and there was an output files directory. It's just, it was just kind of a safeguard in case there was a directory there already. And so currently my computer is trying to take off and it's running the forward simulation through our homogeneous half space model in order to generate our synthetic seismogram. And for one source, one station. So we're only going to get one seismogram out. And that's done. That tells me that it's done. And so if I move on, what I want to do is look at the differences between the two directories that I've just created. So differences between the output files that were created from the checkerboard model and from the homogeneous half space model. You can see here that because we changed that save forward parameter to true, SPECFEM has outputted these files defining the, looks like the absorbing boundary conditions, as well as this important file, which is the last frame of our wave field. And so it needs that file in order to run the adjoint simulation. And this is the same for SPECFEM 2D and 3D. You always need to set that save forward file parameter and before you run your adjoint simulations. And then just for posterity, we can look at the synthetic seismogram that comes out. It's going to look very similar to what we got in our checkerboard, but it's going to have some slight differences, which we're going to quantify in the next section. So there's our synthetic seismogram. Got a single pulse and some little wiggles at the end. If we look at the top of that, which we've shown before in day one, Akash showed this as well. We're just outputting our seismograms in these 2-column ASCII files, which have time on the left column, amplitude on the right column. And so in this next section, 3C, what we're going to do is essentially quantify those data synthetic misfit in order to generate our adjoint sources. We're going to do this manually just to kind of illustrate the point. And this is kind of what Gina talked about in her presentation, is that your choice of misfit function, the way that you choose to define the differences between your data and synthetics has a lot of impact on what your kernels are going to look like, and what, if you use this for imaging, what your updated models should look like. So I'll just plot this here. So I'm just, with this code block, reading in those 2-column ASCII files and plotting them together on a line plot. So you can see here, we're plotting displacement seismograms. The initial, or the synthetics, which we call model init or model initial, those are in black. And those are in red. And our data, the synthetic seismograms that were generated through our checkerboard model, those are in black. And that is sort of a typical color scheme that you might see in computational seismology. Synthetics are red, data is black. It's a little bit hard to see some of those differences. So next code block just zooms in a little bit. So here we can see that the synthetics, the red trace, is slightly different from the target model, the black trace. And so you can imagine that the checkerboard perturbations have essentially caused a bit of a phase advance with respect to the synthetics. So phase delay. So the black data is coming in a little bit later than the red synthetics. And that kind of already tells us, that there's some misfit. So the two models that we're using to generate our data are likely different from one another. So maybe that's a good place to stop. Maybe we can throw a poll up and see if people are looking at this waveform figure.
All right. And
if they have any questions.
Maybe just an audible question. So does this velocity model we're starting with need to be slowed down or sped up? Who wants to try to answer that? You could answer in the chat if you feel like it, or audibly. Does the starting velocity model need to be slowed down or sped up? Here we go. 2 votes for slowed. Yeah. Cool.
Nice.
Mainly it requires thinking about which one is data and synthetic.
Yeah.
It's always kind of confusing, and
it's confusing.
Making a sign error can be pretty devastating, as anyone.
Yeah. It's all over the place. There's so many places to introduce sign errors. So it's fun to try to keep it straight in your head. Okay, so I think we're ready to move on. So we've got about two or three more sections. Excuse me. So section 4, we're going into the misfit quantification. So maybe if I scroll back up to this figure, you can kind of see like, hey, visually, the two waveforms are different. But really, we need to quantify how different are they and what is their differences over time. And so that's the next step, is this misfit quantification. So objective in this section is really to quantify the differences between the red and the black traces using Python in order to then generate our adjoint source. So for A, we're going to do this with Python. We're going to calculate the misfit. So Chinya showed this waveform misfit function, which is just the kind of squared difference between the data and synthetics. So you can imagine in that figure, if you just at every point are taking the squared difference between the red and the black traces, and then integrating over that entire waveform, that would give you kind of a single value that would quantify essentially the differences between those two traces. So that's exactly what we're doing here. We're solving for this value chi, where we're using the true and the data and the synthetic data arrays, and we're just using this Simpson's rule, which is a numerical integration coming out of SciPy. So it's going to give us a single value, which essentially tells us, hey, this is the difference between your data and synthetics based on this equation. And so it doesn't mean too much kind of on its own, but when we get into the imaging stuff and you update a model and you calculate again your data synthetic misfit, that would be how you quantify if you're actually improving your waveform fit. If this value starts going down, which means that the red and the black traces are becoming more similar, then you know that you're doing a good job in improving waveform fits. And then we want to look at the adjoint source, which is just the gradient of the misfit function. So here we're showing you the equation for f dagger, which Jeroen talked about in the first day. It's just the equation for the adjoint source, which is what we're going to inject into our adjoint simulation in order to generate our adjoint wave field. So here you can see this is actually a time-dependent measurement, and it's very simple. It's just synthetic minus data. So here we're doing that and plotting it on top of our synthetic and data waveforms. So here's that same figure that we saw earlier. Now we've got this green trace, which is the adjoint source. And kind of makes sense if you look at it when the two traces are the same. Like for example, when they're both 0, the adjoint source is 0. And the adjoint source peaks when the two are the most different, and peaks again when they're the most different. And so this green trace is really what we are injecting back into our adjoint simulation at our receiver location in order to generate our kernels. And I wanted to make a couple key points here. The first is that each station can have multiple adjoint sources because they can have multiple components. So you can imagine each component would have its own data stream and synthetic waveform. So each then component would have an adjoint source. And so quickly this adds up that you're having to do a lot of different essentially waveform comparisons. If you have lots of sources and lots of receivers, and each of them is like 3 component if you're in a 3D domain. And similarly, you can also window an adjoint source. So if you didn't want to consider these wiggles that are happening out here, you could actually zero out your adjoint source, and it essentially would kind of ignore information that's contained in those wiggles. And this kind of comes back to that question that Carrie had, that you actually don't need to know any of the phases that are coming in here. Like maybe this is direct arrival, but really the adjoint source only cares about the differences here between the two waveforms. And so if you window this area and you feed that into your adjoint source and into your adjoint simulation, you'll get some sensitivity kernel that tells you sensitivity to those wiggles, but you don't really have to know what those wiggles are. Just an aside, a plug for a package that I have written. It's called PyToa. This is a Python-based misfit quantification tool that brings in windowing and adjoint source creation kind of in the context of SPECFEM. So this is just a little code block that runs PyToa, essentially does the same thing, reads in synthetic seismograms, and then compares them. It has some configuration parameters, so you can kind of choose what type of adjoint source you want. You can choose your windowing parameters, and then you can plot and write adjoint sources in the format that SPECFEM is expecting. So it's just gonna send some log messages here, just tell us that things are working. It's telling us that the total misfit value here is 0.003, which is kind of similar to what we had before. And then makes this waveform plot, which is very similar to what we saw earlier. You can see the data in the synthetics here in the adjoint source in the back. Lots of windows, all these orange boxes are windows. And essentially what it's telling us is that the windowing parameters need to be tuned a little bit more. We're just using the default values here. But what it's trying to do under the hood is identify different seismic phases based on this STA, LTA. It's trying to identify different phases so that each of them are windowed separately. And so this kind of comes in a lot more handy when you start looking at real data where things are noisy, where potentially waveform fits for certain phases are really out of line compared to like direct arrivals. Windowing your data in synthetics starts to become more important and more of a useful tool.
Brian, can I make a comment too?
Yeah.
Just to say that, you know, in the case where you have a synthetic experiment like this one, we often know exactly where the arrival is. Like the previous studies with this toy problem, we know the model, so we know where the window is. Whereas this is a very general tool. This windowing tool is much more general and works in realistic noise conditions. But I'm not even sure people have used the automated windowing on synthetic experiments, because in those cases, you often just know where it is and nobody wants to bother. But yeah.
For sure. And often I think in those, oh, sorry, go ahead, Ayra.
No, I just want to make a comment as well. I think, Carl, what you say is correct. My comment is on something different. When it's synthetic experiment, yes, you know what is where, especially for simple models. You may not need windowing, but actually the windowing is also strictly tied to the choice of misfit functions. So for you may not need so many small windows for every misfit function. And I would like to make this comment because there was a question to Chinya about normalization of the measurements, especially considering different moment tensor solutions, different amplitudes, how can you balance the total gradient, etc. And indeed, but if you look at the travel time misfit, there is a natural normalization term that each window, the signal in each window is normalized automatically with a term coming from the adjoint source. But if you have realized in the definition of waveform misfit, there is no normalization term automatically unless you define it yourself in the misfit function. Otherwise, you may have this imbalance between different measurement windows from different paths, different earthquakes, etc. So that's why one way, one convenient way to define the waveform misfit function would be the difference between the synthetic and observed waveforms divided by the energy of synthetics, for instance. That may take care of the normalization.
Definitely, thank you. That's a great point, everyone. That's something that you might see if you would use PyTorch with like a cross-correlation misfit function. You might see the adjoint source here, the amplitude of it blown up really large because it's essentially trying to scale these smaller amplitude arrivals with against the main, more dominant arrivals, so that each one has a more equally weighted influence on the kernels. Cool. Any other questions or discussion points before we move on? Otherwise, this just last code block here is just showing that PyTorch is spitting out adjoint sources that are properly formatted for SPECFEM. So they end in this .80j, which I'll talk about in the next section. And so, if you were just trying to manually run adjoint simulations, you could use that tool in order to create your adjoint sources rather than writing your own Python functions. Great, so we're going to jump into section 5, which is running the adjoint simulation. So just to kind of recap what we've done, we've run a forward simulation through our target model to generate our data. We've run a separate forward simulation through a homogeneous half-space model to generate our synthetics. And then we have calculated an adjoint source based on the 2 synthetic seismograms that we got out. And so now we're actually going to make sure that SPECFEM can find that adjoint source and that the PAR file is set up correctly so that SPECFEM knows to run an adjoint simulation. Running that just to make sure we're in the right directory, and running this code block to write the adjoint source. So in the previous section, we didn't actually write anything. We've now just stored that adjoint source data array in memory. So now we actually have to write it out to a text file that SPECFEM can find. And some important notes here, SPECFEM is expecting the adjoint sources to be located in this SEM directory, SEM standing for spectral element method, I'm pretty sure. And so all of your adjoint sources need to be there so that SPECFEM can find them. They need to be formatted in the same way that your synthetics are. So for us, we have 2-column ASCII files, which define our synthetics. So adjoint sources also need to be 2-column ASCII files with the same time step and start and end times. And then the last important note is that they need to be, their file names need to be formatted the same. So this is the format of our synthetic seismogram. So it's the network station component SEMD. The adjoint source needs to be the same thing, but with that changed to .aj for adjoint. And so just some bookkeeping here, when you create your adjoint sources, they need to be formatted correctly, both inside, and their file name needs to be set correctly. And so that's what we just did here. We made that SEM directory. We just used NumPy in order to generate the kind of 2-column data format. And we're writing that out with the correct file extension. And that's what the top of the adjoint source file looks like. Very similar to the synthetic seismogram. And one really important note here is that SPECFEM. So we talked a lot about how we need to like time reverse our forward wave field or time reverse our adjoint wave field so that they can access, you know, the correct time step during the adjoint simulation. SPECFEM does not expect you to time reverse your adjoint source. So your adjoint source that you're saving into this SEM directory should be running forward in time. And SPECFEM internally will turn it around and reverse it in time. So that's, again, one of these kind of sign flip errors that potentially could crop up if you're not careful. So yeah, now we have all of the correct components, the kind of ingredients for our adjoint simulation. And so we just need to do two more things, set some parameters in our profile and then run SPECFEM again. This is what Akash has talked about in Chinya as well, that we need to tell SPECFEM that we want an adjoint simulation. So we're just telling it to run simulation type 3. And then this is kind of related to the Fortran binary files again. In SPECFEM 2D, we can output kernels in different formats, but really we, in the interest of being very similar to SPECFEM 3D, we're gonna ask it to output things in Fortran binary rather than in ASCII. And then we can run our adjoint solver. And we're gonna do kind of the same thing, redirect the text file output, and then have a look at what the adjoint solver tells us. And this is gonna take a little bit longer than a forward simulation would, since it's doing a lot more calculations. It's doing, you know, the interaction field as well as the summation of the kernel. So generally, I think in my work, I've seen adjoint simulations taking something like 1.5 times the length of a forward simulation. So keep that in mind when if you're like running on a cluster and you need to specify your wall time. That's kind of a good rule of thumb in order to figure out a new wall time for your adjoint solver. Any questions up to that point? We're getting pretty close to the end of this notebook. What we're going to do is then look at the outputs of our adjoint simulation, and we're going to regularize the output, the kernel, and then kind of we're getting close on time, but maybe we can release you into the exercise and look at maybe one of the first two tasks.
Go ahead, Luis.
Yeah, Luis.
Yeah, I have a question related to the normalization of the adjoint sources that Avery was mentioning. So is it safe to think that you want to normalize the adjoint source when you're comparing the kernels for two different phases? But let's say that I want to compare the kernel for one station, compare it against another station, but for the same phase. Would I have to normalize the adjoint source as well? Maybe let's say that one station it's within a sedimentary basin and it gets amplified. So the kernel, the adjoint source would be larger than the other one. So would I have to normalize that as well?
Well, actually, this normalization I refer to is more for the inversion part. So actually, the amplitude of your kernels will be directly controlled by the amplitude of your phases. So whatever amplitude you have, you will have the corresponding kernel. Think it like this. But then when you merge all these or sum up all these kernels that you compute for individual phases, for different, recorded at different stations and for multiple earthquakes, you know, you just simply sum them up to construct your gradient. And in that case, if there are, as you gave the example of sedimentary basins, you will have you may have significantly amplified waves propagating through some specific geological structures, or depending on the radiation pattern, this and that, or depending on the epicentral distance, you know, amplitudes are controlled by various different factors. You may have some bias towards in your total gradient towards those high amplitude phases, right? And you don't really want to have such an unbalanced gradient when you start updating your models or perform iterations. Because, you know, the success of your inversions will depend on multiple factors. One of them will be having a good data coverage and a balanced gradient. So actually what I refer to as you need to normalize these measurements is more for the inversion part, not to compare the amplitudes of different kernels for different phases, because that's not so difficult to understand that the amplitude of phases will directly control the amplitude of, not only the amplitudes, of course, the misfit, the value of misfit.
So for example, if we wanted to compute the kernel for 3 different stations, like separately, and then average them to obtain the adjoint kernel, would we have to normalize individual kernels or just like sum them up?
Otherwise, yeah, that would be better. Otherwise, rather than the value of the misfit, specific kernels might be highlighted depending on, or not highlighted, let's put it, let's say it in the reverse order. Assume that you are making measurements on body waves and surface waves. You use both body and surface waves in the inversion. You know, surface wave amplitudes are always large. Even if you have the same amount of time shift between your body wave phase and the surface waves, let's say 2 seconds, it doesn't matter. If you don't normalize those measurements, you are going to have much larger amplitudes of adjoint sources for surface waves. And the total kernel will be always dominated by surface waves. So you won't be able to take advantage of using body waves in your inversions in that case. Everything will be dominated by surface waves. Your iterations will update only the upper part of your model throughout iterations until you may have 0 misfit for the surface wave part, which in practice is extremely difficult. Maybe that may be a better example, that to be able to take better advantage of low amplitude phases in your inversions, normalization is much better.
But I just wanted to add that give the impression there isn't much choices to make. I mean, once you set the misfit function, I don't know if we're saying the same thing, but the example with the body waves and surface waves with the cross correlation measurement in that expression, the normalization factor is to account for that fact that a tiny amplitude body wave will get more count because, you know, before the weight is even applied due to how big it's fitting, if you have like a 5-second measurement on surface versus body wave. So the theory kind of handles all that exactly how you want it to. And so one thing to
emphasize, it's only for the travel time misfit.
Right,
it's like,
right.
Or the waveform misfit,
okay.
You need to adapt your misfit.
Sure. So the travel time, though, the dominant safe route that a lot of people have used takes that into account, so that a tiny little amplitude body wave will get a lot of weight. You know, you basically identify that as something important in the measurement. Yeah. Misfit functions. Thanks to both of you.
So that's why you can find a huge literature on the definition of misfit functions, either to linearize the inverse problem, which will be discussed tomorrow, or to speed up the convergence rate, etc., for different reasons.
Thank you.
Cool. Yeah, super interesting discussion. And yeah, you could get lost in the rabbit hole of misfit functions for sure. It's a big part of this. But just for our example, we're going to use a very simple waveform difference because we're looking at synthetic seismograms that are pretty well behaved. So now we're going into section 5C, which is hopefully you've already finished running the adjoint simulation. So we're just going to look at the outputs of that simulation. So what I'm doing here is just doing a little bit of bookkeeping so that we can use the SeisFlows plotting tool in order to look at our kernel. I'm renaming some of these kernels from alpha to VP, beta to VS. This is just to make things a little bit more intuitive when you look at the names of the kernels. So just moving a little files there, and then I'm going to run this to create a plot, which is plotting the VS kernel and then putting our source and station on top of it so that we can see if it makes sense. And so there is the raw kernel that came out of our adjoint simulation, which is proportional to essentially the interaction of the forward wave field. And if I scroll up against the adjoint source that we generated here. So that this green trace was injected at the receiver location to create an adjoint wave field. This was propagated against the forward wave field that we generated earlier. And the resulting kind of volumetric integration leaves us with this scar-shaped kernel. And this kind of leads us into the fact that we want some regularization. You can see some like fringe patterns here. You can see like probably not see, but under the source and station markers, there's a little bit of high amplitude. This is what Gina talked about, I think what Akash talked about, that if you have these point representations of your source and station, which we do in the simulation, you're going to get some kind of essentially like asymptotic behavior right around them. So typically what we do is do some kind of regularization. And so like I promised earlier, we're going to do some smoothing of this kernel using one of SPECFEM's internal tools. But before that, there's just two of these image code blocks that, if you remember from day one, we were plotting the forward wave field. This also just shows the adjoint wave field. So if I zoom out really quickly and try to get back to where I was. Here you can see the receiver. You can see the source down here. And now in this adjoint simulation, actually the receiver, we're injecting that adjoint source at the receiver location. If we go a little bit further in time, you can see it propagating outwards. And if you had multiple adjoint sources in your simulation, I'm pretty sure you would see multiple kind of wave propagations coming out. So finally, this is the last section, section 6. I'll zoom in again. We're going to smooth and regularize this kernel. That's the last kind of task that we're going to have today for this notebook. And so idea being, again, we want to use this internal smoothing tool, which is called XSmoothSem. It's the same in SPECFEM 2D and 3D. And the idea is that we're convolving whatever quantity when we want to put in with a Gaussian. Here it's a 2D Gaussian. In SPECFEM 3D, it's a 3D Gaussian. And this is the kind of run call usage that you might expect. You're running with MPI if you have a split up into multiple processors, and then you're choosing the half width in the horizontal direction, that's that sigma H, and the half width in the vertical direction, that's the sigma V. So you're controlling the essentially the shape and the size of this 2D Gaussian, and then you're telling SPECFEM, hey, I want to smooth this quantity, and some paths to tell it where to look for files and where to put its smooth files. And so this is that code block. So running MPI just with one core, running the XSmoothSem. We're choosing 5 kilometer half widths, just as kind of a initial guess value. We're asking it to smooth the VS kernel. So that's what we're going to look at. And then just telling it that we can find the kernel files here in the output files directory. And the last flag here is for GPU mode. And so smoothing can be quite a bottleneck in adjoint simulations, in seismic inversions. And the developers of SPECFEM have put in a lot of work in order to accelerate things using GPUs. So if you've compiled the code on a GPU, you can set that to true and it'll use GPU acceleration to speed up the smoothing operation significantly. So I'm going to run this. Hopefully it doesn't take too long because we're running a pretty small smoothing Gaussian. It's going to output some text files here telling us what the half width and the kind of full scale length of the 2D Gaussian are. And then these are just, again, some more bookkeeping, making sure that the files get moved somewhere safe. And the output files that are of the smooth kernels get this underscore smooth suffix. So we're just going to kind of get rid of that and look at the final kernel, which has been smoothed using SizeFlows. We're going to use the utility function again to just plot that VS kernel, which has now been smoothed. And while that's running, maybe I'll just talk about section 7. I don't think we're going to run it today, but for those who are interested in automated tools, here's an example of using size flows to essentially automate an adjoint simulation. This runs the exact same setup we just did. So sorry, things are moving. It runs the exact same setup that we did. So it's doing this checkerboard versus homogeneous half space model. And the actual workflow is trying to do a full inversion. We're just telling it to stop after it makes the kernels. And then the other code blocks down here visualize the model and the kernels that come out of there. But here is that smooth kernel. And so you can see that we've created this cigar-shaped kernel. We got rid of some of those fringe patterns with our smoothing. We could probably smooth a little more aggressively if we wanted to get rid of some of these, the kind of singularities that are coming below the sources and receivers. So this is something you can either kind of think about theoretically or try to do with trial and error, trying to find like the optimal smoothing length that corresponds to like the scale lengths that you think you can resolve with your waveform data, with the kind of bandpass that you're putting into your input data. It's kind of a research grade question of like, how much do I need to regularize my kernel? And you can see, yeah, somebody says that the output does not have the same color bar scale, so you can actually see that the smoothing has reduced the amplitude. So if I make a note of here, this is 1e to the minus 12. If I go up to back to this kernel, this is 1e to the minus 11. So we've actually reduced some of the amplitudes because we're kind of, the smoothing you can think of as like spreading around and kind of smearing out a lot of the amplitude information here. Okay, so that was the end of notebook 2A. And we're kind of pushing up on the hour here. So potentially we could just open it up for discussion. And I think the exercises are a nice thing to do, and we might try to revisit those tomorrow. Something that I wanted to leave with is that, when you answer the day 2 survey today, please try to let us know if you're interested in some of these exercise materials, if you want us to kind of go through them rather than just running through notebooks, and we can try to cater tomorrow's workshop material to kind of go with what people are interested in.
Thanks, Brian. Has anyone, let me ask a question here. The question for the poll is, was this the first kernel you've ever made before, yes or no? And that'll combine 2 questions of, did it actually work for you? And was it new to you? So is this the first kernel you've ever made before? That's the question. Relaunch poll. I don't know how, I really don't know what to expect here, but either you've already done this before, or we'll see if we can get, there's still 92 of you. Thank you very much for sticking it out this long, but I may have to save this poll because I feel like this is an actual, even though the question is, are you ready to move on? I think for ourselves, yeah, we've got, I'll share these results. So 41 out of 51, 81% says this is the first kernel they've ever made. I think that's really cool. Hopefully we could actually turn that into like doing something useful with it. But as you saw earlier, I mean, just looking at certain kernels can, in some cases, be a publication because it gives you insights into these wiggles that we're working with. All right, I'm gonna actually save that one and then share. So there you go. Wrong question, but I think it kind of drives home the point that it's not that easy to do some of this stuff, and especially what the big thing is for tomorrow is you've got zillions of these. However, each measurement has one of these kernels under the hood, so you might have tens of thousands or hundreds of thousands of these to take into account. How should we wrap this up, Brian? Do you want to point to where the 2B? Do you want to just point it out?
Yeah, I can maybe point it out and show what it is. Depending on how the surveys go, we might revisit this tomorrow, but just so you're kind of introduced to it. So this is just below 2A here in the kernel, in the notebook directory. Hopefully that opens soon. So the idea behind this notebook is really just to kind of take everything that we learned in day 1A, or day 1 and day 2, in order to run your own kernel simulation. And so there's a lot of, there's a little bit of introduction here, and then the idea here is this is the only code block that you would have to execute that we've already pre-written. Just sets up this working directory where you've got your binary data and par file, and just sets up the par file kind of correctly so that you don't have to think about that. And then really there's just tasks here. So first task would be, let's set some stations. And there's a variety of approaches that you could take. So you could go for the easiest approach and just say, hey, I want to use the already preset stations. I put a number of 25 here, but really you could use all of the 132 stations if your heart desired. And then more moderate approaches, you can generate your own stations file using Python or whatever your favorite kind of programming language of choice. And there's a little bit more advanced approaches like, hey, let's create a really interesting station configuration. Let me create some concentric rings or something that I've seen that's really exotic in publications. And then kind of following on that, you're creating your source, and there's also different approaches, running the mesh and solver, and hopefully try to put a lot of reminders and notes in there so that you don't feel completely lost. But I will just emphasize that there are also solutions here in case you get stuck and want to kind of take a glimpse at how you might approach the problem. And by the end of it, you will hopefully have quantified misfit between two synthetics or between all your synthetics, and generated an adjoint generated a misfit kernel after running your adjoint simulation. And so hopefully, you could run through that on your own with the help of the exercise solutions. And if there's some interest, we can have a look at that tomorrow as well. Maybe run through it slowly.
And Bryant, where was that example you did where you could just like change the event and get a different kernel from the old example? Was that day 0?
That was in day 0. Yeah.
Okay, so
you want me to show that?
Well, we've hit some tasks that are now more relevant, having introduced things. No,
yeah.
That's sort of an even easier change. Yeah. I was just thinking that as we approach the end here, so people can potentially, we could spend more time, and we could go into breakout rooms tomorrow and actually like work through these choose your own adventure. So on the survey, kind of comment on where you'd like to see the last day go if you want to. I will put, before I do sign off on the recording, I'm going to put just, it's the workshop webpage link, which I know is, you run the risk of not finding the link, but from the workshop webpage, click on day 2. That'll give you the survey, and I'll send another reminder just to get track of who's here. What else do we need to say at this point? Yeah. The red text at the bottom would take us there.
Yep, day 2 survey here. Yeah, maybe we can, I have some time. We can like stick around and have discussion if people have questions or are interested in talking about more specific topics.
Yeah, I think what we'll do is I'll stop the recording, and just to say for the record, yeah, I think we had a great turnout, something like 142 start, and the survivors here, the last 90 are finishing. So thank you so much for sticking through it. I'll stop the recording, but then anyone who wants to